Hello there, and welcome to Science for Sleep, where curiosity slows down, questions soften, and science is allowed to unfold without urgency. Tonight we are settling into a subject that feels familiar on the surface, yet becomes strangely uncertain the longer you sit with it. Time. Not the version printed on your phone screen or blinking on a microwave, but the deeper idea we quietly rely on without ever checking whether it behaves the way we assume. We plan our lives around it. We complain about having too little of it. We wait for it to pass and wish we could hold on to it. And yet, when physics looks closely, time turns out to be far less solid than it appears. Before we wander too far into that thought, take a moment to notice where you are. Perhaps you are lying down, or sitting somewhere comfortable, or letting the day loosen its grip a little. What time is it where you are right now, and where in the world are you listening from? It is always quietly amusing that a conversation about time arrives at many different moments at once, each listener anchored to their own clock, their own evening, their own slice of the rotating planet. If you find this kind of slow exploration calming or gently interesting, you might consider liking the video or subscribing. It helps this quiet corner reach others who are also looking for a softer way to end the day. There is no rush. Nothing here needs to be remembered or mastered. The ideas will drift past at a human pace. We often speak about time as if it were obvious. Seconds tick forward. Minutes accumulate. The past sits behind us. The future waits ahead. This picture feels so natural that questioning it can seem unnecessary. After all, time works well enough for cooking dinner, catching a bus, or deciding when to go to sleep. But physics has a habit of unsettling ideas that feel too comfortable. When scientists began to examine time not as a background assumption, but as something to be tested, measured, and placed inside equations, the familiar picture began to slip. For a long time, the dominant idea in physics was simple. Time was universal. It flowed at the same rate everywhere, for everyone, no matter what they were doing or where they were located. This view reached its most polished form in the work of Isaac Newton. In his framework, time existed independently of the physical world. Objects moved through space, forces acted on them, events occurred, and time provided a steady backdrop against which all of this unfolded. It did not speed up or slow down. It did not care what was happening. It simply passed. This idea was not unreasonable. In everyday experience, clocks tend to agree with one another. If two people synchronize their watches and go about their day, they can meet again and find that their watches still match. Trains run according to schedules. Mechanical systems behave predictably. Newton's equations described motion with remarkable accuracy, from falling apples to orbiting planets. Time, in this picture, functioned like an invisible ruler for change. Reliable, unquestioned, always there. Because it worked so well, the assumption of absolute time became deeply embedded, not just in physics, but in culture. We began to treat time as a resource, something that could be saved, spent, wasted, or borrowed. Entire systems of work, education, and industry were built on the idea that time ticked forward uniformly, dividing the day into identical slices that could be filled with activity. For centuries, there was little reason to doubt this structure. The first serious cracks appeared when scientists turned their attention to light. In the 19th century, experiments showed something unexpected. No matter how fast an observer was moving, the measured speed of light remained the same. This result was not a small inconvenience. It directly conflicted with the idea of absolute time. If time were truly universal, then speeds should add together in simple ways. A person moving toward a beam of light should measure that light as moving faster. Yet this did not happen. At first, physicists tried to preserve the old picture by adding new assumptions. Perhaps light travelled through an invisible medium. Perhaps clocks subtly adjusted themselves. But none of these fixes held up. Eventually the problem was addressed directly by Albert Einstein. Instead of forcing light to obey classical time, he allowed time itself to change. In Einstein's special theory of relativity, published in 1905, Time was no longer a single universal quantity. It became something tied to motion. Observers moving at different speeds could disagree about the timing of events. Two flashes of light that appeared simultaneous to one observer might not be simultaneous to another. This was not a trick of measurement or a flaw in instruments. It was a fundamental feature of how time works. One of the consequences of this shift is time dilation. When an object moves very fast relative to another, the passage of time for that object slows down. This effect is not psychological, it is physical. Clocks carried aboard fast-moving aircraft tick more slowly than identical clocks left on the ground. Atomic clocks placed on satellites must be corrected to account for their motion. Without these corrections, navigation systems would drift out of alignment within minutes. Motion, then, affects time. This alone is enough to dismantle the idea that time is the same everywhere. But relativity did not stop there. A decade later, Einstein extended his ideas to include gravity. In general relativity, gravity is not treated as a force in the usual sense. Instead, massive objects curve space-time itself. And because time is part of space-time, gravity affects how time passes. The stronger the gravitational field, the more slowly time flows. A clock closer to a massive object ticks more slowly than one farther away. This effect has been measured on Earth. Clocks placed at higher altitudes run slightly faster than clocks at sea level. The difference is small, but real. Once again, time refuses to behave as a single shared backdrop. By this point, the old picture of time as a universal river flowing steadily forward has become difficult to maintain. Time stretches. Time compresses. Time depends on speed and gravity. It behaves less like a rigid framework and more like something woven together with space and matter. Despite this, everyday life remains largely unaffected. At the speeds we move and the gravitational fields we experience, relativistic effects are tiny. For practical purposes, time still behaves as if it were absolute. This is why Newton's picture continues to work well for most engineering and daily tasks. The deeper truth, however, is that this apparent simplicity hides a more complex structure. As physics continued to advance, another challenge emerged, this time from the microscopic world. Quantum mechanics, the theory that describes particles at very small scales, treats time in a curious way. In most quantum equations, time appears as an external parameter. It ticks forward uniformly, much like Newton's time, even while everything else behaves probabilistically. Space becomes uncertain. Energy fluctuates. Particles exist in superpositions. Yet time marches on untouched. This creates a tension. General relativity tells us that time is dynamic, shaped by gravity and motion. Quantum mechanics treats time as fixed and absolute. When physicists attempt to combine these two theories into a single framework, time becomes problematic. In some approaches to quantum gravity, time disappears from the fundamental equations altogether. One of the most striking examples is an equation intended to describe the entire universe at the quantum level. In this equation, there is no time variable. The universe is described as a static object, not evolving in time at all. This does not mean that change does not occur. It means that change must be understood differently, without relying on a background clock. At this point, it becomes reasonable to ask whether time is truly fundamental. Perhaps time is not a basic ingredient of reality, but something that emerges from more primitive relationships. Just as temperature emerges from the motion of many particles, time might emerge from correlations between physical systems. In this view, time is not something the universe contains. It is something we infer. This idea is unsettling, but it aligns with an important observation. We never measure time directly. We measure change. A clock does not detect time itself. It tracks the motion of hands, the vibration of atoms, the oscillation of a crystal. Time is inferred from regular patterns. If nothing changed, time would be indistinguishable from absence. This perspective also helps explain why time feels directional. The fundamental laws of physics, with a few exceptions, do not care about the direction of time. They work just as well forward as backward. Yet our experience of time has a clear arrow. We remember the past. We anticipate the future. Causes precede effects. Physics traces this asymmetry not to time itself, but to entropy. Entropy is a measure of how energy is distributed. Systems tend to evolve from states of lower entropy to states of higher entropy. This statistical tendency gives rise to the arrow of time. Time appears to flow because the universe began in a state of unusually low entropy and has been increasing ever since. From this angle, time's direction is not a fundamental rule. It is a consequence of initial conditions. The laws themselves remain symmetrical. The asymmetry enters through the history of the universe. All of this leads to a quiet but profound conclusion. Time is not what it seems. It is not a universal ticking metronome. It is not an independent backdrop against which reality unfolds. It bends with motion. It slows near mass. It may not exist at the deepest level at all. And yet, it structures every experience we have. As these ideas settle, there is no need to resolve them or hold on to every detail. The important thing is not to arrive at an answer, but to notice the shift in perspective. Time, which once seemed obvious, has become a question. A useful question. One that physics continues to explore from many directions. Long before anyone worried about satellites correcting their clocks or particles slipping in and out of existence, time felt reassuringly straightforward. It behaved the way people expected it to behave. It moved forward. It moved evenly. It did not ask questions, and it did not require explanation. In the classical view of physics, time was something you could trust without hesitation, like the steady turning of the earth, or the predictable rise and fall of the sun. You did not need to wonder whether it might slow down, stretch, or behave differently depending on where you stood. Time was simply there, quietly keeping order. This way of thinking did not emerge by accident. It grew out of daily experience. When early scientists observed the world, they saw patterns that repeated with remarkable regularity. A pendulum swung back and forth. The moon completed its cycle. Seasons followed one another in a stable rhythm. If you measured how long something took today, and then measured it again tomorrow, the result was usually the same. These observations encouraged a powerful assumption. Time itself must be uniform. It must pass at the same rate everywhere, regardless of what was happening within it. By the 17th century, this assumption had been formalized into a coherent framework, most famously through the work of Isaac Newton. In Newton's physics, time occupied a special role. It was not treated as something created by motion or change. Instead, it existed independently of the physical universe. Objects moved through space. Forces acted upon them. Events occurred. But time flowed on its own, unaffected by any of it. Newton described time as absolute, true, and mathematical. Those words were chosen carefully. Absolute meant that time did not depend on anything else. True meant that it existed whether or not anyone measured it. Mathematical meant that it could be represented precisely, allowing equations to describe motion with exactness. In this picture, time resembled an invisible, perfectly reliable clock ticking away somewhere beyond the universe, setting the pace for everything within it. This idea of a universal clock made physics elegant. If time passed at the same rate everywhere, then it provided a common reference against which all motion could be compared. Two events happening at different locations could be said to occur at the same time without ambiguity. Velocities could be calculated simply by dividing distance by time. Acceleration became the change in velocity over time. The equations worked because time behaved consistently. Crucially, this was not just a theoretical convenience. It matched how the world seemed to work. If two people synchronized their clocks and then went their separate ways, they would later find that their clocks still agreed, assuming neither had been damaged. The success of mechanical clocks reinforced the belief that time itself was mechanical in nature. Gears turned, pendulums swung, springs oscillated. The clock's steady rhythm appeared to mirror the rhythm of time itself. As clocks improved, confidence grew. By the 18th and 19th centuries, timekeeping had become central to navigation, industry, and daily life. Sailors relied on accurate clocks to determine longitude. Factories organised labour by the hour. Trains followed timetables that demanded precise coordination. All of this rested on the assumption that time was the same everywhere, ticking forward identically in every town, every city, every ship at sea. Within classical physics, there was no reason to doubt this structure. Newton's laws of motion worked astonishingly well. They could predict the trajectory of a cannonball, the swing of a pendulum, and the orbit of a planet. When discrepancies arose, they were usually traced to measurement errors or unaccounted forces, not to time itself. Time was not questioned, because it did not appear to misbehave. Even when philosophers debated the nature of time, physics remained largely unaffected. Some thinkers argued that time was nothing more than a way of ordering events. Others believed it was a fundamental aspect of reality. These debates were interesting, but they did not interfere with calculations. As long as time could be treated as a uniform parameter, the machinery of classical physics ran smoothly. One reason this picture felt so natural is that it aligns closely with human perception. We experience time as a steady flow. The past feels fixed. The future feels open. The present feels like a thin, moving boundary between the two. Classical physics fit neatly into this intuition. It offered a universe where events unfolded on a shared timeline, accessible to everyone in the same way. The notion of simultaneity was especially important. In the classical view, if two events occurred at the same time, then they occurred at the same time for everyone, everywhere. There was no need to ask who was observing or how fast they were moving. Time provided a universal now, slicing the universe into moments that could be labelled and agreed upon. This assumption simplified communication and coordination. If a bell rang at noon, then it was noon everywhere, adjusted only by local conventions of timekeeping. Differences in longitude could be corrected by adding or subtracting hours, but the underlying idea remained intact. Time zones existed, but time itself was still universal. The clock face might differ, but the ticking behind it was assumed to be the same. Classical physics also treated time as reversible in principle. The equations describing motion did not care whether time ran forward or backward. If you replaced time with its negative in most classical equations, they still worked. A planet could orbit clockwise or counterclockwise. A pendulum could swing left to right or right to left. This symmetry suggested that time itself was neutral, merely a parameter labelling change. Despite this mathematical symmetry, everyday experience introduced a sense of direction. Things aged, objects wore down, memories accumulated. But classical physics did not attempt to explain this directionality. It treated time as a coordinate, not as a process with a preferred direction. The arrow of time was considered a separate issue, belonging more to thermodynamics than to mechanics. Within this framework, the universe resembled a perfectly wound clock. Given enough information about the positions and velocities of all particles at a single moment, the entire future and past could, in principle, be calculated. Time provided the parameter along which this calculation unfolded. The universe evolved, but time itself did not change. This deterministic vision was both powerful and comforting. It suggested that nature followed clear rules, and that uncertainty was merely a consequence of incomplete knowledge. Time, in this picture, was not mysterious. It was the canvas on which the universe painted its predictable patterns. Yet even within classical physics, subtle questions lingered. If time flowed independently of everything else, what exactly was it flowing through? If the universe were empty, with no objects and no change, would time still pass? Newton believed it would. Time, for him, did not require events to exist. It flowed whether or not anything happened. Not everyone agreed. Philosophers such as Gottfried Wilhelm Leibniz argued that time was relational, not absolute. According to this view, time was nothing more than the order of events. Without events, there would be no time. But classical physics did not need to resolve this disagreement. Its equations work equally well regardless of which interpretation one preferred. As long as the speeds involved were modest and gravity behaved predictably, the classical picture remained unchallenged. Time could be treated as universal without contradiction. It could be synchronized, divided, and trusted. The success of this approach made it feel not just useful, but true. What is easy to forget is that this confidence was built on a limited range of experience. Classical physics described a world of everyday speeds, familiar scales, and gentle gravitational fields. Within that domain, time behaves in ways that closely resemble our intuition. It is only when we step beyond those boundaries that the cracks begin to show. At the edges of classical understanding, certain assumptions quietly waited to be tested. What happens to time when objects move extremely fast? What happens when gravity becomes very strong? What happens at scales too small to observe directly? Classical physics did not provide answers to these questions, because it did not yet know they needed to be asked. Still, the idea of time as a universal clock shaped scientific thinking for centuries. It influenced how experiments were designed, how data were interpreted, and how theories were constructed. Even today, much of engineering and applied science continues to rely on this approximation, because it works well enough for most purposes. The key point is not that the classical picture of time was wrong in every sense. It was incomplete. It captured an aspect of reality that holds under many conditions, but it mistook that usefulness for universality. Time behaves like a steady clock, only within a certain range of circumstances. Outside that range, it reveals a different character. As physics progressed, it would encounter situations where treating time as absolute led to contradictions. Measurements would refuse to align. Equations would produce conflicting results. Something would have to give. And when it did, it would not be space or matter that yielded first, but time itself. For now, though, it is worth lingering with the classical view just a little longer. It provided the foundation upon which later revolutions were built. Without it, the deviations would not have been noticeable. You cannot discover that something bends unless you first believe it is straight. For a long stretch of scientific history, the idea that time was absolute did not feel like an assumption at all. It felt like a fact so obvious it barely needed stating. Physics believed time was absolute because in every practical sense available at the time it behaved that way. Experiments agreed, calculations aligned. Daily experience reinforced it. And perhaps most importantly, nothing appeared to contradict it. To understand why this belief became so deeply embedded, it helps to look at what physics was trying to do in its early modern period. The goal was not to question the nature of reality at its deepest level, but to describe motion, forces, and change in a way that was consistent, predictive, and mathematically precise. Time, in this context, was not the subject of investigation. It was a tool. When early physicists studied falling objects, projectiles, or planetary motion, they needed a parameter that could label change. Something had to mark when an object was here and when it was there. Time served this role perfectly. It increased steadily. It could be divided into equal parts. It allowed motion to be expressed as distance covered per unit time. Once that framework was in place, it worked extraordinarily well. One of the strongest reasons time was treated as absolute is that classical experiments showed no dependence of time on motion. If two observers moved relative to one another at everyday speeds, their clocks still agreed. If someone walked, rode a horse, or sailed a ship, time did not seem to behave differently for them than it did for someone standing still. From the standpoint of available measurement, time appeared immune to motion. This matters because physics builds its confidence on repeatability. If you perform an experiment today and repeat it tomorrow under the same conditions, the outcome should be the same. Classical physics delivered this reliability. A pendulum swung with a predictable period. A ball rolled down an incline in a way that could be measured again and again. Time entered these experiments as a stable background quantity. It did not introduce variability. The absence of observable time effects reinforced the belief that time itself was unaffected by physical processes. Space could be stretched or compressed. Objects could speed up or slow down. Forces could change direction. Time, however, seemed to remain untouched. It was not pushed, pulled, bent, or altered by anything within the system. Another reason physics embraced absolute time lies in the structure of Newton's laws themselves. These laws describe how objects move when forces act on them. They require a time variable that behaves smoothly and consistently. Acceleration, for example, is defined as the rate of change of velocity with respect to time. If time behaved differently in different places or for different observers, this definition would become ambiguous. Newton's equations assume that when you write down a time variable, it means the same thing everywhere. This assumption is not stated as a hypothesis. It is built directly into the mathematical framework, and because the framework produced correct predictions across a vast range of phenomena, the assumption remained unchallenged. There was also no experimental motivation to question it. Classical physics dealt with speeds far slower than the speed of light, and gravitational fields far weaker than those found near extreme objects. Under these conditions, any deviations from absolute time are so small that they are effectively invisible. Clocks remain synchronized. Durations match expectations. Time behaves exactly as assumed. The development of increasingly precise clocks further strengthened confidence in absolute time. Mechanical clocks, and later pendulum clocks, demonstrated remarkable consistency. Two clocks built the same way and placed in different locations would keep time together as long as environmental conditions were controlled. This consistency suggested that clocks were tapping into something real and universal, not merely producing an arbitrary measurement. As clocks became portable, they were used to coordinate activities over larger distances. Railways depended on synchronized schedules. Communication networks relied on agreed-upon times. The success of these systems depended on time behaving uniformly across space. And since they worked, the assumption seemed justified. Even astronomy reinforced the idea. The motions of planets could be predicted far into the future using a single time variable. Eclipses could be calculated centuries in advance. Comets returned on schedule. These successes relied on the idea that time passed at the same rate everywhere in the solar system. There was no hint that a clock on Earth and a clock on Mars would tick differently. From a philosophical standpoint, absolute time also offered clarity. It allowed physicists to define simultaneity without ambiguity. If two events occurred at the same time, then they occurred at the same time for everyone. There was no need to specify an observer or a frame of reference. Time provided a universal ordering of events. This universality simplified the description of causality. Causes preceded effects in a well-defined sequence. The temporal order of events was fixed and objective. Disagreements about which event happened first were assumed to arise from incomplete information, not from differences in perspective. The belief in absolute time was also influenced by the broader intellectual climate. The scientific revolution sought laws that were universal, objective, and independent of human perception. Absolute time fit neatly into this worldview. It existed whether or not anyone observed it. It flowed whether or not anything happened. It provided a neutral framework for describing reality as it truly was. Importantly, classical physics did not distinguish between measured time and true time. The assumption was that a well-built clock measured time accurately. any discrepancies between clocks were attributed to mechanical imperfections, not to time itself behaving differently in different circumstances. This assumption held until measurement techniques became sensitive enough to reveal tiny discrepancies that could not be explained away. But before that point, there was simply no reason to suspect that time might be relative, flexible, or dependent on physical conditions. Another factor that reinforced absolute time was the separation between space and time in classical physics. Space was three-dimensional. Time was one-dimensional. They were treated as fundamentally different entities. Space could be navigated. Time could not. Space allowed motion in different directions. Time allowed only forward progression. This separation made time feel simpler and more stable. While space could be distorted by perspective, time seemed immune. An object could be closer or farther depending on where you stood, but an hour was an hour regardless of location. At least that was how it appeared. The mathematical formalism reflected this separation. Coordinates describe positions in space. Time was an independent variable. It did not mix with spatial coordinates. This structure made calculations manageable and intuitive, and again, because it worked, it was trusted. Thermodynamics, which introduced concepts like entropy and irreversibility, did not immediately challenge absolute time either. While it introduced a preferred direction for processes, it did not suggest that time itself flowed differently for different observers. The arrow of time was treated as a statistical feature of physical systems, not a property of time itself. As a result, physics developed a layered picture. Mechanics described motion using absolute time. Thermodynamics described irreversibility within that same temporal framework. Electromagnetism described fields evolving over time. All of these theories assumed the same underlying clock. When disagreements arose between theory and experiment, time was rarely suspected. Other factors were examined first: measurement error, environmental interference, unaccounted forces. Time was the last thing anyone thought to question. This confidence is understandable. To question time is to question the reference frame of all measurement. It undermines the very language in which physical laws are expressed. Doing so requires not just new data, but a willingness to rethink foundational concepts. For centuries, physics did not need that willingness, because nature did not demand it. Only when experiments involving light produced results that refused to fit the classical framework did time begin to look less solid. The speed of light appeared constant in all frames of reference. This single fact carried enormous implications. If the speed of light is the same for all observers, then either space or time, or both, must adjust to accommodate that constancy. Classical physics assumed space and time were fixed. Something had to give. Before that realization took hold, physicists tried to preserve absolute time by introducing new entities or modifying existing assumptions. They proposed invisible media through which light travelled. They adjusted equations in ad hoc ways. These efforts reflect just how deeply the belief in absolute time was rooted. It was not abandoned lightly. It had earned its place through centuries of success. It matched intuition. It matched observation. It matched mathematics. Only overwhelming evidence could dislodge it. What eventually became clear is that absolute time is an excellent approximation within a limited domain. At low speeds and weak gravitational fields, time behaves as if it were universal. This is why the classical picture remains useful. It captures the behavior of time in the regime where humans evolved and built their first technologies. The mistake was not believing in absolute time, but believing it was fundamental. Physics once believed time was absolute because everything it could see and measure supported that belief. The universe did not reveal its subtleties until measurements became precise enough and questions bold enough to expose them. By the late 19th century, physics appeared confident, even comfortable with its understanding of the universe. Space was a vast, stable stage. Time flowed evenly in the background. Matter moved according to clear laws. There were open questions, of course, but nothing that suggested the foundations themselves were unstable. And then, almost quietly, light began to cause trouble. Light had always been a curious subject. It was fast, far faster than anything humans could move or throw or propel with engines of the time. But for a long while that speed was treated as just another large number, impressive but not conceptually threatening. Once measured, it was assumed to behave like any other speed, add motion to the source, subtract motion from the observer, and the result should adjust accordingly. This expectation fit neatly into the classical picture of time as absolute. The first careful measurements of the speed of light suggested something surprising. No matter how the measurement was performed, light appeared to travel at the same speed. Whether the observer was moving toward the light source or away from it, the result did not change. At first, this seemed less like a revolution and more like an irritation. Perhaps the experiments were flawed. Perhaps some subtle factor had been overlooked. To understand why this result was so unsettling, it helps to recall how speeds normally behave. If you are standing still and someone throws a ball toward you, you measure the ball speed directly. If you start walking toward the thrower, the ball reaches you faster, and you measure a higher speed. If you walk away, the ball takes longer, and you measure a lower speed. This simple rule applies to cars, trains, sound waves, and flowing rivers. Classical physics had no reason to expect light to behave differently, yet repeated experiments suggested that it did. One of the most famous was performed by Albert Michelson and Edward Morley in 1887. At the time, physicists believed that light travelled through an invisible medium called the luminiferous ether. This ether was thought to fill all of space, providing a reference frame against which light's motion could be measured. If Earth moved through this ether, then the speed of light should vary depending on the direction of measurement, much like wind affects the speed of sound. Michelson and Morley designed an experiment sensitive enough to detect this variation. They split a beam of light into two perpendicular paths, recombined them, and looked for interference patterns that would indicate a difference in speed. As Earth moved through space, the orientation of the apparatus changed, and so should the measured speed of light along each path. The result was unexpected. No difference appeared. The speed of light was the same in all directions. The ether, if it existed at all, was undetectable. This outcome was not just puzzling. It directly challenged the idea that time and space provided a fixed background for motion. At first, physicists attempted to save the classical picture. Some proposed that objects physically contracted in the direction of motion through the ether, exactly enough to cancel out the expected differences. Others suggested that clocks slowed down when moving through the ether. These ideas were not derived from deeper principles. They were patches, designed to preserve absolute time while accommodating inconvenient data. What these fixes had in common is that they treated time as something that could be adjusted locally, without challenging its universal nature. Time was still assumed to be fundamentally the same everywhere. The discrepancies were blamed on the behaviour of matter and measuring devices, not on time itself. But the pattern persisted. No experiment could detect motion relative to the ether. Light always moved at the same speed, regardless of the observer's state of motion. This was not a minor anomaly. It was a fundamental inconsistency between observation and expectation. The deeper problem lay in how speed is defined. Speed is distance divided by time. If the speed of light is the same for all observers, then either distances change, time changes, or both. Classical physics assumed both distance and time were fixed. Light was telling physicists that this assumption could not hold. In 1905, Albert Einstein took a different approach. Instead of asking how to preserve absolute time, he asked what would happen if the constancy of the speed of light were taken seriously as a fundamental principle. He proposed two simple postulates. First, the laws of physics are the same in all inertial frames. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion. These postulates were radical not because they introduced something new, But because they refused to introduce anything extra, there was no ether, no hidden reference frame, just the insistence that light behaves the way experiments say it does. From these assumptions, a startling conclusion followed. Time could no longer be absolute. If observers moving relative to one another both measured the same speed of light, then their measurements of time must differ. There was no way around it. One of the first casualties of this realization was simultaneity. In classical physics, simultaneity was universal. Two events either happened at the same time or they did not. In Einstein's framework, simultaneity became relative. Events that appeared simultaneous to one observer could occur at different times for another observer moving at a different speed. This was not a matter of perception or delayed signals. It was built into the structure of space-time itself. Each observer carried their own definition of what counted as now, determined by their state of motion. Time dilation emerged naturally from this framework. A moving clock runs more slowly than a stationary one, as measured by the stationary observer. This effect is not due to mechanical strain or environmental interference. It applies equally to atomic clocks, biological processes, and radioactive decay. Time itself is passing differently. Length contraction accompanied it. Objects moving at high speed appear shortened along the direction of motion. Space and time adjust together to preserve the constancy of the speed of light. What is striking is how gently these conclusions follow from the initial problem. There is no dramatic leap. Once light's behaviour is accepted, absolute time simply cannot survive. The cracks appear not through philosophical debate, but through arithmetic. Importantly, these effects are not noticeable at everyday speeds. You do not experience time dilation while walking down the street. The difference is far too small. This is why classical time appeared so reliable for so long. The cracks were always there, but they were microscopic within the range of human experience. As technology advanced, these effects became measurable. Atomic clocks flown on airplanes ticked more slowly than those on the ground. Particles moving near the speed of light decayed more slowly than expected when measured from a stationary frame. These were not theoretical predictions waiting for confirmation. They were observed facts. The speed of a light had exposed a limit. It was not just a speed limit for objects moving through space. It was a structural feature of space-time itself. Nothing could exceed it because doing so would require time and space to behave in ways that violate their interdependence. This realization forced physics to abandon the idea that time flowed independently of the physical world. Time became something that could stretch and compress depending on motion. It was no longer the same everywhere. At this stage, gravity had not yet entered the picture. The cracks in time were already significant. Motion alone was enough to show that time could not be universal. Yet even this partial shift was difficult to absorb. It required abandoning deeply ingrained intuitions about what it meant for events to occur at the same time. One reason this shift was so unsettling is that time had always served as a universal coordinator. It allowed events separated by vast distances to be placed on a single timeline. Once that timeline fractured, coordination became relative. Each observer carried their own clock, equally valid, equally real, yet not universally aligned. Despite this, the new framework was not chaotic. It was precise. It replaced one set of assumptions with another, more accurate one. Instead of absolute time, there was space-time, a unified structure in which space and time were inseparable aspects of a single whole. In this structure, the speed of light plays a central role. It defines how space and time are related. It sets the scale at which classical intuitions break down. It is not just a property of light, but a feature of space-time itself. What began as a puzzling measurement became a turning point. The speed of light did not merely challenge existing theories. It revealed that time, long assumed to be rigid and universal, was flexible and observer-dependent. For most of human history, simultaneity felt like one of the safest ideas anyone could hold. Two things happened at the same time, or they did not. The concept required no special training, no equations, no philosophical patience. If two bells rang together, they rang together for everyone. If lightning struck in two places at once, then it struck at once, regardless of who happened to be watching. This assumption slipped so naturally into everyday thinking that it was rarely spoken aloud. It did not feel like a belief, it felt like a definition. Classical physics inherited this intuition without resistance. If time was absolute, then simultaneity followed automatically. A single universal clock meant a single universal present. Events could be lined up along a shared timeline, and their temporal relationships were fixed. Disagreements about timing were treated as errors of measurement or communication delays, not as fundamental differences in reality. This idea was so deeply embedded that even questioning it seemed unnecessary. Why would simultaneity ever depend on who was observing? Either something happened at noon, or it did not. Physics, after all, aimed to describe the world as it truly was, not how it appeared from different perspectives. A universal present fit that ambition perfectly. The first cracks did not appear through philosophical debate, but through the behaviour of light. Once the speed of light was shown to be the same for all observers, regardless of motion, the assumptions underlying simultaneity quietly began to fail. At first, this failure was not obvious. The equation still worked. The clock still ticked. But when physicists tried to reconcile constant light speed with absolute time, contradictions emerged. To see why simultaneity could not survive unchanged, it helps to think carefully about how we decide whether two distant events happen at the same time. Imagine two lightning strikes hitting the ground at two different locations. How do we determine whether they were simultaneous? One approach is to place an observer exactly halfway between them. If the light from both strikes reaches that observer at the same moment, the strikes are declared simultaneous. This method seems reasonable, but it relies on an assumption. It assumes that light travels at the same speed in both directions and that the observer is not moving relative to the events. In classical physics, these assumptions are unproblematic. Space is fixed, time is universal, light behaves like any other wave. Now imagine the same setup, but the observer is moving. Perhaps they are riding a train that passes between the two lightning strikes. If the speed of a light is constant for all observers, then the moving observer will still measure light travelling at the same speed from both directions. However, because the observer is moving toward one flash and away from the other, the light from one strike will reach them before the light from the other. According to the moving observer, the two lightning strikes did not occur at the same time. One happened earlier than the other. There is no experimental error here. The observer's measurements are internally consistent. Their clocks function properly. Light behaves as expected. Yet their conclusion about simultaneity differs from that of the stationary observer. Classical physics would dismiss this difference as an illusion caused by motion. It would insist that there is a true answer to the question of simultaneity, and that one observer must be mistaken. But Einstein's framework does not allow that dismissal. If the laws of physics are the same for all inertial observers, then no observer has privileged access to the truth. Both perspectives are equally valid. This is where simultaneity breaks. There is no longer a single correct answer to whether two distant events happened at the same time. The answer depends on the observer's state of motion. Simultaneity becomes relative. This result is not a semantic trick. It is a direct consequence of how time and space adjust to preserve the constancy of the speed of light. In order for light to travel at the same speed for all observers, clocks in different locations must be synchronized differently depending on motion. There is no universal way to synchronize distant clocks that works for everyone. Clock synchronization, which once seemed like a technical detail, suddenly becomes central. In Einstein's framework, synchronizing clocks involves sending light signals back and forth and assuming that light takes the same time to travel in both directions. But because observers in relative motion disagree about distances and durations, they also disagree about whether clocks are synchronized. This disagreement does not arise because clocks malfunction. It arises because time itself is not shared in the way classical physics assumed. Each observer carries their own temporal framework, shaped by their motion. The consequences of this shift are subtle but profound. Events that are simultaneous in one frame of reference are not simultaneous in another. This means that the ordering of events in time is not absolute. For some pairs of events, different observers will disagree about which one happened first. It is important to note that this disagreement does not apply to all events. If one event can causally influence another, meaning a signal travelling at or below the speed of light can connect them, then all observers will agree on their order. Still precedes effect. Relativity preserves causality. The disagreement arises for events that are too far apart for light to travel between them in the time separating them. These events are said to be space-like separated. For such events there is no causal connection, and therefore no universal ordering. One observer may say event A happened first, another may say event B happened first. Both descriptions are correct within their respective frames. This realization forces a re-evaluation of what the present moment means. In classical thinking, the present was a slice through the universe, containing all events happening now. In relativity, there is no such slice that everyone agrees on. Each observer has their own present, defined by their motion. The idea of a universal now dissolves. There is no single moment that all of space shares. Instead, there is a collection of observer-dependent nows, each equally valid, none privileged. This is deeply counterintuitive because human experience is confined to very low speeds. At everyday velocities, the differences in simultaneity are so small that they are impossible to notice. For practical purposes, simultaneity appears universal. The classical picture remains an excellent approximation. But physics is not concerned only with approximations. It seeks underlying structure. And at that level, simultaneity is not a fundamental feature of reality. It is a relationship that depends on how an observer moves through space-time. Space-time is the key word here. Once space and time are understood as parts of a single, four-dimensional structure, simultaneity loses its independent status. Different observers slice space-time into space and time in different ways. What one observer calls space at a given moment includes events that another observer assigns to different times. This slicing is not arbitrary. It is governed by precise mathematical relationships. Lorentz transformations describe how coordinates in space and time change between observers in relative motion. These transformations replace the simpler Galilean transformations of classical physics, which assumed time was the same for everyone. Under Lorentz transformations, time mixes with space. An interval that is purely temporal for one observer may include spatial separation for another. This mixing is the mathematical expression of relativity of simultaneity. Once this structure is accepted, many other relativistic effects follow naturally. Time dilation and length contraction are not separate phenomena. They are consequences of how different observers divide space-time into space and time. The loss of universal simultaneity also reshapes how events are described globally. In classical physics, one could speak of the state of the universe at a given time. In relativity, this concept becomes frame-dependent. The state of the universe now depends on who is asking. This does not mean physics becomes subjective. The laws remain objective and consistent. What changes is the recognition that certain quantities once thought to be absolute are in fact relational. Time ordering, simultaneity, and duration depend on relationships between observers and events. This realization has implications beyond thought experiments. It affects how systems are synchronized across distances. Technologies like GPS must account for relativistic effects to function correctly. Satellites moving relative to Earth experience time differently, and their clocks must be adjusted to maintain accuracy. More conceptually, the relativity of simultaneity challenges deeply held intuitions about reality. It undermines the idea that there is a single unfolding story of the universe, shared identically by all observers. Instead, there are many consistent stories, each told from a different perspective. This does not fragment reality into disconnected pieces. All observers agree on the outcomes of experiments and on causal relationships. What they disagree on are the labels attached to events, specifically their timing relative to other distant events. It is tempting to think of this as a limitation of measurement, but that misses the point. The disagreement is not about what is observed locally. It is about how distant events are related in time. There is no deeper layer in which simultaneity is restored. Once simultaneity stops being universal, time itself begins to look less like a flowing substance and more like a coordinate within a structure. It becomes something that helps organize events rather than something that exists independently of them. This shift also sets the stage for later developments. If simultaneity is relative, then the idea of a universal present loses meaning. This opens the door to interpretations of reality in which past, present, and future are not fundamentally distinct, but are instead different regions of space-time. Such ideas will become more explicit when gravity enters the discussion. Gravity further complicates time by causing it to flow at different rates in different locations. But even before that, the loss of universal simultaneity is enough to dismantle the classical picture. It is worth emphasizing that none of this implies that time is an illusion or that events are unreal. What it implies is that temporal relationships are not absolute features of the universe. They depend on motion and geometry. In everyday life, this dependence is negligible. The Earth moves slowly compared to the speed of the light. Gravitational fields are relatively weak. Simultaneity appears reliable. But at high speeds and large distances, the differences become significant. Physics does not discard everyday experience. It explains why everyday experience works the way it does and where its limits lie. The classical notion of simultaneity works because the conditions under which it fails are rare in daily life. As understanding deepened, physicists began to see that what felt like a breakdown was actually a refinement. The universe was not becoming less orderly. It was revealing a more nuanced order, one that required letting go of assumptions that had outlived their usefulness. With simultaneity no longer universal, time itself becomes woven into the structure of space-time. Motion affects how time is divided. Observers do not share a single clock. They share laws that relate their measurements consistently. Once the idea of universal simultaneity quietly slipped away, it left behind a space where new questions naturally formed. If observers moving relative to one another cannot agree on whether distant events occur at the same time, then the structure of time itself must depend on motion in a deeper way. This realization does not arrive suddenly or dramatically. It settles in gradually, like noticing that a familiar road has a subtle slope you never felt before. The concept that follows from this shift is one of the most famous and most misunderstood results of modern physics. Time slows down with motion. At first glance, this statement sounds metaphorical, or even exaggerated. Time slowing down suggests something physical happening to time itself, as though it were a fluid thickening under strain. Classical intuition resists this immediately. Motion, after all, changes where you are, not how fast time passes. A person walking, riding or flying does not feel time behaving differently. Their watch ticks normally. Their heartbeat stays steady. Nothing in daily experience hints that motion has any influence on the passage of time. And yet, when the constancy of the speed of light is taken seriously, this conclusion becomes unavoidable. Time slowing down with motion is not an extra assumption layered onto relativity. It is a direct consequence of insisting that light behaves the same way for all observers. To see how this arises, it helps to imagine a very simple clock, not a mechanical one with gears and springs, but a clock built from light itself. Picture two mirrors facing each other, with a pulse of light bouncing back and forth between them. Each round trip of the light pulse marks one tick of the clock. This device is often called a light clock, not because it is practical, but because it makes the logic transparent. Now imagine this clock at rest relative to you. You see the light pulse travel straight up and down between the mirrors. The distance between the mirrors is fixed, and the speed of the light is constant, so the time it takes for the pulse to complete a round trip is well defined. The clock ticks at a steady rate. Next, imagine the same clock moving horizontally at a constant speed relative to you. From your perspective, the light pulse is no longer travelling straight up and down. Instead, it follows a diagonal path. While the light moves upward toward the top mirror, the entire clock is moving sideways. By the time the light reaches the mirror has shifted horizontally. On the return trip, the same thing happens in reverse. From your frame of reference, the light travels along a path between ticks. Importantly, the speed of light does not change. Light always moves at the same speed, regardless of the motion of its source or the observer. If the distance the light travels increases and the speed remains fixed, then the time required for each tick must increase. The moving clock ticks more slowly than the stationary one. This is not because the clock is damaged or malfunctioning. It is because time itself is passing more slowly for the moving system relative to you. This conclusion is not dependent on the type of clock. The light clock is just a convenient illustration. Any clock, whether based on atomic vibrations, radioactive decay, or biological processes, must exhibit the same effect. If one type of clock slowed down due to motion while another did not, it would be possible to detect absolute motion, which would contradict the principle that the laws of physics are the same for all inertial observers. Time dilation, as this effect is called, applies universally. Motion affects time itself, not the mechanism measuring it. At this point, it is natural to ask whose time is actually slowing down. From the perspective of the stationary observer, the moving clock runs slow, but from the perspective of the moving observer, their own clock ticks normally. It is the stationary observer's clock that appears to be running slow. This symmetry is not a contradiction. It reflects the fact that there is no absolute state of rest. Motion is always relative. Each observer considers themselves at rest and sees the other as moving. Time dilation is reciprocal for observers in uniform relative motion. This reciprocity often causes confusion, especially when imagining scenarios involving travel and aging. The key is that time dilation is not about one clock being objectively slower. It is about how time is measured between different frames of reference. Each observer's proper time, the time measured along their own path through space-time, is locally normal. The mathematics describing this effect is precise. The factor by which time slows down depends on the relative speed between observers. As speed increases, the effect becomes more pronounced. At everyday speeds, it is imperceptible. At speeds approaching the speed of light, it becomes dramatic. If an object could move arbitrarily close to the speed of light, time for that object would slow down dramatically relative to a stationary observer. Processes would unfold more slowly. Decay rates would decrease. Aging would slow. From the object's own perspective, however, nothing unusual would occur. Its internal processes would proceed normally. This result has been confirmed experimentally many times. Particles produced in high-energy accelerators live longer than they would if they were at rest. Their extended lifetimes match the predictions of time dilation precisely. Atomic clocks flown around the Earth on aircraft or placed aboard satellites tick more slowly than identical clocks on the ground, exactly as relativity predicts. These experiments leave little room for interpretation. Time dilation is not a theoretical curiosity. It is a measurable, repeatable effect. One of the most famous illustrations of time dilation is often referred to as the twin paradox, though there is nothing paradoxical about it once the details are understood. One twin remains on Earth, while the other travels into space at high speed and then returns. When they reunite, the travelling twin has aged less than the one who stayed behind. The crucial detail is that the travelling twin changes frames of reference when turning around to return. Their motion is not symmetrical with that of the twin on Earth. The asymmetry resolves the apparent contradiction. The travelling twin follows a different path through space-time, one with less accumulated proper time. What matters here is not motion alone, but the geometry of space-time paths. Time dilation is not just about speed, it is about how different trajectories through space-time accumulate different amounts of time. This geometric perspective is essential. In relativity, time is not something that flows independently of motion. It is part of space-time, and different paths through space-time have different lengths in time, just as different paths through space have different lengths in distance. Once this idea is accepted, time dilation becomes less mysterious. It is not that time is being stretched or compressed by some force. It is that time is measured along world lines, and those world lines differ depending on motion. The idea that motion affects time forces a re-evaluation of what clocks really measure. A clock does not measure some universal time flowing everywhere. It measures the proper time along its own path. Two clocks following different paths through space-time will, in general, record different amounts of time between the same pair of events. This realization breaks completely with the classical picture. In classical physics, time was something all clocks measured equally, regardless of their history. In relativity, time becomes path-dependent. Despite how strange this sounds, it fits naturally with the structure introduced earlier. Once simultaneity is relative, it follows that duration must also be relative. If observers disagree about which events are simultaneous, they cannot agree universally on how long intervals between distant events last. It is worth emphasizing again that this does not lead to chaos. Relativity provides exact rules for relating measurements between observers. Time dilation is not arbitrary. It follows a precise mathematical relationship determined by relative velocity. The deeper significance of time slowing down with motion is not just that clocks tick differently. It is that time itself is no longer separate from the dynamics of the universe. Motion, once thought to take place within time, now actively shapes time. This shift has consequences for how we think about processes unfolding in the universe. It suggests that time is not a passive stage, but an active participant in physical phenomena. The rate at which things happen depends on how they move. At the same time, it's important to notice what time dilation does not do. It does not allow anyone to outrun time entirely. It does not permit travelling faster than light. As speed increases, the energy required grows without bound. Time slows, but it never stops completely for any object with mass. This limit reinforces the role of the speed of light as a fundamental boundary. It is not just a speed limit for motion. It is a conversion factor between space and time, setting how they trade off against each other. From a human perspective, the effects of time dilation are almost always negligible. We live at speeds so slow compared to light that time behaves classically. This is why the classical picture persisted for so long. The universe allowed us to believe in absolute time because the deviations were too small to notice. But physics is concerned with what is true, not just what is noticeable. When experiments reached regimes where these effects could no longer be ignored, time revealed its flexibility. The realization that motion slows time also prepares the ground for an even more surprising development. If motion can affect time, then gravity, which influences motion and energy, should also have an effect. And indeed, gravity does more than slow objects down or pull them inward. It alters the rate at which time itself passes. Before moving fully into that territory, it helps to sit with the implications of motion-based time dilation a little longer. It tells us that time is not a single entity shared by all observers. It tells us that duration depends on trajectory. It tells us that the universe does not provide a master clock ticking uniformly in the background. Instead, time becomes something local. Each object carries its own time with it, shaped by how it moves through space-time. These local times can be related, compared and transformed, but they are not identical. This is not an abstract conclusion. It affects how we design technology, how we interpret astronomical observations, and how we understand high-energy processes in the universe. Without accounting for time dilation, Modern navigation systems would fail. Without it, particle physics would not make sense. Once motion revealed that time does not pass at the same rate for all observers, it might have been tempting to think the disruption was complete. Velocity alone seemed radical enough. After all, the idea that simply moving fast could slow the passage of time overturned centuries of assumption. Yet motion turned out to be only half the story. There was another influence, quieter and far less intuitive, that affected time just as deeply, even when nothing appeared to be moving at all. That influence was gravity. At first, gravity does not seem like something that should have anything to do with time. In everyday experience, gravity pulls objects downward, keeps planets in orbit, and gives weight to physical things. Time, by contrast, feels abstract and detached from such forces. Classical physics reinforced this separation. Gravity acted on masses. Time flowed independently in the background. The two occupied different conceptual categories. This separation did not survive closer examination. When Einstein extended relativity to include gravity, he discovered that gravity is not merely a force acting within space and time. It is a manifestation of how space and time themselves are shaped by mass and energy. Once this shift occurs, it becomes unavoidable that gravity must influence time directly. To understand how this happens, it helps to move away from the image of gravity as an invisible pull, and instead think in terms of geometry. In general relativity, massive objects curve space-time. Space and time are not separate entities stitched together loosely. They form a single structure, and mass alters that structure. A useful way to picture this is to imagine space-time as a flexible surface. Place a heavy object on it, and the surface bends. Objects moving nearby follow paths shaped by this curvature. What is less obvious, but equally important, is that the curvature affects not only spatial paths, but temporal ones as well. Time does not flow at the same rate everywhere on a curved surface. Near a massive object, time passes more slowly than it does farther away. This effect is known as gravitational time dilation. Unlike the time dilation caused by motion, which depends on relative velocity, gravitational time dilation depends on position within a gravitational field. What makes this effect especially striking is that it applies even when nothing is moving. Two clocks can be at rest relative to one another, completely stationary, and still disagree about how much time has passed if they are located at different gravitational potentials. Imagine one clock placed on the surface of the Earth and another placed high above it, perhaps on a satellite. Both clocks are functioning normally. Neither is moving relative to the other in any significant way. Yet the clock closer to Earth's mass ticks more slowly than the one farther away. This is not a mechanical effect. The clock is not being squeezed or distorted. Its internal processes proceed as usual from its own perspective. The slowing of time is not something the clock experiences locally. It is something that appears when its time is compared to that of a clock in a weaker gravitational field. This effect has been measured directly. Highly precise atomic clocks placed at different altitudes on Earth show measurable differences in their ticking rates. Even a height difference of a few meters is enough to produce a detectable change with modern instruments. Time, quite literally, passes faster on a mountain than at sea level. At first, this seems almost trivial, a tiny correction of little practical importance, but its conceptual implications are enormous. It means that time is not only relative to motion, but also to location. There is no single rate at which time passes across space. To see why gravity affects time this way, it helps to recall the equivalence principle, one of the foundations of general relativity. This principle states that locally, the effects of gravity are indistinguishable from the effects of acceleration. Standing in a gravitational field feels the same as being in an accelerating frame. Consider an elevator in deep space, far from any massive objects. If the elevator accelerates upward, a person inside feels pressed against the floor, just as they would on Earth. From inside the elevator, it is impossible to tell whether the force they feel is due to gravity or acceleration. Now imagine two clocks inside this accelerating elevator, one at the floor and one at the ceiling. Light signals sent between the clocks behave differently due to the acceleration. From the perspective of an observer inside, the clock at the ceiling appears to tick faster than the one at the floor. By the equivalence principle, the same must be true in a gravitational field. The clock higher up, in a weaker gravitational field, ticks faster than the one lower down. Gravity affects the flow of time. This reasoning shows that gravitational time dilation is not an add-on to relativity. It is woven into its core. Once gravity is understood as geometry rather than force, time's variability with position becomes unavoidable. The stronger the gravitational field, the more pronounced the effect. Near extremely massive objects such as neutron stars or black holes, the difference becomes dramatic. A clock near the surface of a neutron star would tick significantly more slowly than a clock far away. Near the event horizon of a black hole, time slows so much relative to distant observers that it appears to nearly stop. This does not mean that time actually stops for an object falling into a black hole. From the object's own perspective, time passes normally. The dramatic slowing is a comparison effect, observed from far away. This distinction is important. Relativity does not claim that time itself freezes locally. It claims that comparisons between different regions of space-time reveal differences in accumulated time. Once again, time is revealed as something local rather than global. Each clock measures its own proper time. Comparing clocks requires accounting for how space-time is curved between them. Gravitational time dilation also introduces a subtle asymmetry into the universe. While motion-based time dilation is reciprocal between observers in uniform relative motion, gravitational time dilation is not symmetric in the same way. A clock deeper in a gravitational well always ticks more slowly relative to one higher up. There is no frame in which this reverses. This asymmetry arises because gravitational fields have structure. They are not just relative relationships between observers. They reflect the presence of mass and energy shaping space-time itself. This difference has practical consequences. Modern navigation systems rely on satellites orbiting Earth. These satellites experience weaker gravity than clocks on the ground, which causes their clocks to tick faster. At the same time, their motion causes time dilation that slows their clocks down. Both effects must be accounted for. If they were not, the system would accumulate errors of kilometers within a single day. This is one of the clearest demonstrations that gravitational time dilation is not a theoretical curiosity. It is an operational reality. Technology works because physics has learned how to calculate how time flows differently in different places. Beyond practical applications, gravitational time dilation reshapes how we think about aging, history, and duration. In principle, two people who live their lives at different gravitational potentials will age at different rates. Someone who spends decades in orbit will be slightly younger than someone who remains on the surface of the Earth. The difference is tiny under Earth's gravity, but it is real. In stronger gravitational environments, it becomes significant. Near a massive object, life would unfold more slowly relative to distant regions of the universe. This introduces an unsettling but fascinating idea. The universe does not share a single age. Different regions accumulate time at different rates. Asking how old the universe is becomes a subtle question, dependent on where and how the measurement is made. This does not mean that age becomes meaningless. It means that age, like time itself, is contextual. It depends on the path taken through space-time. Another important implication is that gravity links time directly to energy. In general relativity, energy, including mass, determines the curvature of space-time. That curvature determines how time flows. Time is therefore influenced by energy distribution throughout the universe. This connection suggests that time is not a passive parameter, but an active feature of physical reality. Changes in mass and energy distribution affect the geometry of space-time, which in turn affects temporal relationships. At this point, the classical picture of time has been thoroughly dismantled. Time is not universal. It is not uniform. It does not flow independently of the physical world. It slows with motion. It slows near mass. It depends on geometry. Yet even now the picture is not complete. General relativity describes how gravity shapes time beautifully at large scales, but it does not explain everything. When gravity becomes extremely strong and quantum effects become important, the behaviour of time becomes even more mysterious. Before reaching that frontier, it is worth lingering with the implications of gravitational time dilation a bit longer. It suggests that time is woven into the structure of the universe in a way that defies simple metaphors. It is not a river flowing everywhere at the same speed. It is more like a landscape, where the rate of flow depends on the terrain. This landscape is smooth and gentle under ordinary conditions. On Earth, the differences are barely noticeable. This is why our intuitions remain largely classical. The universe allows us to live comfortably with approximations, but the deeper truth remains. Time is not evenly distributed. It bends, stretches, and slows in response to gravity. This realization also prepares the ground for another conceptual shift. If gravity affects time because it curves space-time, then space and time cannot be treated as separate arenas. They are inseparable aspects of a single structure. This structure responds to matter and energy dynamically. Understanding time therefore requires understanding space-time as a whole. Isolating time from space leads to confusion. Their behaviours are linked. Gravity's influence on time is not loud or dramatic in everyday life. It does not announce itself with visible effects. It works quietly, consistently, shaping the passage of seconds without ever asking for attention. Yet it reveals something profound. Time is not a background against which gravity acts. Time is one of the things gravity shapes. By the time gravity's influence on time becomes clear, a quiet realization has already taken hold. Treating time and space as separate, independent things no longer works. The effects of motion and gravity have made that separation increasingly artificial. Time changes with speed. Time changes with location. Space changes as well. Distances contract. Paths bend. Trying to keep space and time in different conceptual boxes begins to feel like forcing a map onto terrain it no longer fits. This is where the idea of space-time enters, not as a poetic metaphor but as a practical necessity. Space-time is not a new substance added to the universe. It is a way of describing reality that acknowledges what experiments and equations have been quietly insisting all along. Space and time are not two separate stages on which physics happens. They are woven together into a single structure, and physical events are best understood as occurring within that structure as a whole. In classical physics, space and time had very different roles. Space was something you could move through freely in three directions. Time was something that moved forward relentlessly in one direction. You could stop in space. You could turn around. You could change direction. Time offered no such freedom. It flowed uniformly and independently, indifferent to what happened within it. Relativity dissolves this distinction. Once the speed of light is taken as fundamental, space and time must adjust together to preserve it. Neither can remain fixed while the other adapts. They become linked, mathematically and physically. To understand this linkage, it helps to think not in terms of motion alone, but in terms of events. An event is something that happens at a specific place and a specific time. A lightning strike, a particle collision, a clock ticking. In relativity, events are the basic building blocks of reality. Space-time is the collection of all events, organized in a four-dimensional structure. 3 dimensions correspond to space. 1 corresponds to time. Every event has coordinates in this four-dimensional framework. Where classical physics would describe an object's history as a path through space over time, relativity describes it as a single continuous path through space-time, called a world line. This shift in description is subtle but powerful. Instead of imagining objects moving through space as time passes, relativity invites us to see objects as tracing paths through space-time. Time is no longer something that flows independently. It is one of the directions within which motion occurs. This does not mean time becomes interchangeable with space. The time dimension has different properties from the spatial ones, but they are connected in ways that cannot be ignored. Transformations between observers mix space and time coordinates. What one observer calls a difference in space, another may call partly a difference in time. This mixing is not optional. It is required by the structure of space-time itself. Lorentz transformations replace the older Galilean transformations precisely because space and time are not independent. When observers move relative to one another, their measurements of space and time adjust in linked ways. The key quantity that remains invariant across observers is not space alone or time alone, but the space-time interval. This interval combines spatial separation and temporal separation into a single measure. Different observers may disagree about distances and durations, but they agree on the space-time interval between events. This invariance reveals something important. Space-time is not just a convenient bookkeeping device. It has physical significance. It encodes the relationships between events in a way that remains consistent across perspectives. Once space-time is taken seriously, many previously puzzling results fall into place. Time dilation and length contraction are no longer strange distortions imposed on clocks and rulers. They are natural consequences of how different observers slice space-time into space and time. Each observer defines their own notion of what counts as space at a given moment and what counts as time passing. These definitions correspond to different ways of slicing space-time into spatial and temporal directions. None of these slices is more correct than another. They are simply adapted to different states of motion. This geometric viewpoint also clarifies why there is no universal present. The present moment corresponds to a slice through space-time that an observer labels as now. Different observers, moving differently, slice space-time differently. Their present moments include different sets of events. There is no global slice that all observers agree on. Space-time does not come with a built-in notion of simultaneity. That notion emerges only once an observer chooses a particular frame of reference. When gravity enters the picture, space-time becomes not just a static structure, but a dynamic one. Mass and energy tell space-time how to curve. Curved space-time tells matter how to move. This relationship is the core of general relativity. In this framework, gravity is no longer a force acting across space. It is a manifestation of space-time geometry. Objects follow the straightest possible paths called geodesics through curved space-time. What we perceive as gravitational attraction is simply the result of objects moving along these paths. Time is inseparable from this geometry. The curvature of space-time affects not only spatial trajectories, but also temporal ones. The rate at which time passes depends on the shape of space-time at a given location. This explains gravitational time dilation in a natural way. Near a massive object, space-time is curved more strongly. Paths through time accumulate differently there than in regions of weaker curvature. Clocks lower in a gravitational field trace shorter temporal intervals between the same events than clocks higher up. Seen this way, gravitational time dilation is not a mysterious slowing imposed by gravity. It is a geometric effect. Different regions of space-time have different temporal geometry. The idea of space-time as a single interwoven fabric also reshapes how distance is understood. Distance is no longer purely spatial. It depends on how space-time is sliced. Two observers may disagree about the distance between events, just as they disagree about the time between them. Yet these disagreements are not arbitrary. They are constrained by the structure of space-time. Observers can transform their measurements into one another's frames using precise rules. Physics remains consistent because the underlying space-time structure remains the same. This unified view also helps explain why the speed of light occupies such a central role. Light follows paths through space-time that define its structure. The speed of light sets the scale that links space and time together. It determines how much space can be traded for time and vice versa. In space-time diagrams, which physicists use to visualize these relationships, light always travels at a 45-degree angle. This angle is the same for all observers. It reflects the invariant nature of the speed of light and the geometry of spacetime itself. Within these diagrams, the effects of time dilation, length contraction, and relativity of simultaneity become geometric facts rather than mysterious behaviours. They emerge naturally from how different observers tilt their axes through spacetime. This geometric interpretation is not merely aesthetic, it has practical power. It allows physicists to predict the behaviour of systems under extreme conditions, such as near black holes or in the early universe. Near a black hole, space-time curvature becomes extreme. Paths through space-time bend sharply. Time slows dramatically relative to distant observers. Spatial distances behave in unfamiliar ways. None of this requires new forces or exotic mechanisms. It follows from the geometry. Space-time also provides a framework for understanding horizons. An event horizon is not a physical surface in space. It is a boundary in space-time, separating events that can influence an observer from those that cannot. This boundary arises because of how space-time is curved by mass. In this context, time plays a crucial role. Events inside a horizon are not simply hidden behind a spatial barrier. They are separated in time-like ways that prevent signals from reaching certain observers. Understanding space-time as a single fabric also changes how we think about the universe as a whole. Instead of imagining the universe evolving moment by moment, one can imagine the entire space-time structure existing as a four-dimensional entity. Events are laid out within it, connected by causal relationships. This viewpoint, sometimes called the block universe perspective, does not imply that change is illusory. It implies that change is represented by relationships between events, rather than by a universal flow of time. Motion and evolution are encoded in the geometry of space-time. Whether or not one adopts this interpretation philosophically, the mathematical framework of relativity supports it naturally. The equations describe space-time as a whole, not as something unfolding in an external time. This does not mean that experience is irrelevant. Humans experience time locally. We remember the past. We anticipate the future. These experiences correspond to how our world lines pass through space-time, and how our brains process information along those paths. Space-time does not deny experience. It contextualizes it. It explains why time feels uniform locally, while varying globally. It explains why our intuitions work at everyday scales and fail at extreme ones. Importantly, space-time is not a substance in the traditional sense. It does not flow. It does not ripple like fabric unless described mathematically in terms of curvature changes. The fabric analogy is useful, but it should not be taken too literally. Space-time is a structure defined by relationships, not a material thing. Still, the interwoven nature of space and time is real. It shows up in experiments, technology, and astronomical observations. It governs how clocks tick, how signals propagate, and how objects move. Once this picture is accepted, it becomes clear that asking what time is, independent of space, is no longer a well-posed question. Time is one aspect of space-time. It cannot be fully understood in isolation. This realization marks a turning point. Earlier, time was shown to slow with motion. Then it was shown to slow with gravity. Now it becomes clear why. Time is not being acted upon from the outside. It is part of the same structure that motion and gravity shape. Seeing space and time as interwoven does not make the universe simpler, but it makes it coherent. The strange behaviours of time are not arbitrary quirks. They are expressions of a deeper structure. Once space and time are understood as a single interwoven structure, it becomes clear that their behaviour cannot be uniform everywhere. If space-time responds to mass and energy, then regions containing extreme concentrations of mass or energy must distort that structure in equally extreme ways. Time, being part of space-time, cannot escape this influence. It behaves differently not because it chooses to, but because the geometry it inhabits changes. Under ordinary conditions, these differences are subtle. Earth's gravity slows time by tiny amounts. Satellites drift slightly out of sync. Mountain clocks run imperceptibly faster than sea level ones. These effects are real, but they remain comfortably small, allowing daily life to proceed as though time were universal. Extreme objects, however, do not grant that comfort. Near them, the assumptions that quietly supported intuition begin to fail. Extreme objects in physics are defined not by drama, but by density and scale. Neutron stars, black holes, and the early universe itself qualify because they pack enormous amounts of mass or energy into very small regions of space-time. In these environments, curvature becomes intense. The geometric rules governing space-time no longer produce gentle bends. They produce steep gradients, deep wells, and boundaries beyond which familiar descriptions lose meaning. Time responds directly to this curvature. Near extreme objects, it does not merely slow by a fraction of a percent, it slows dramatically when compared to distant regions. In some cases, the difference becomes so large that comparing clocks across regions requires careful interpretation, because what one observer calls seconds, another would call vastly longer intervals. To understand why this happens, it helps to recall that in general relativity, gravity is not a force acting through space. It is the shape of space-time itself. Objects follow paths determined by that shape. Time, measured along those paths, accumulates differently depending on how space-time is curved. Consider a neutron star. These objects are the remnants of massive stars that have collapsed under their own gravity. A neutron star can contain more mass than the Sun compressed into a sphere only a few tens of kilometers across. The result is an intense gravitational field. Space-time around a neutron star is sharply curved. A clock placed near the surface of a neutron star would tick much more slowly than a clock far away. This is not because the clock is damaged by gravity or squeezed by pressure. It is because the geometry of space-time near the neutron star allocates less temporal distance between events than the geometry far from it. This difference is not hypothetical. It is a direct prediction of general relativity. In principle, if two observers compared notes after one spent time near a neutron star and the other remained far away, they would find that different amounts of time had passed for each. Black holes take this behaviour to its extreme limit. A black hole forms when mass is compressed into such a small region that space-time curvature becomes so steep that not even light can escape from a certain boundary, known as the event horizon. This boundary is not a physical surface, it is a feature of space-time geometry. As an object approaches a black hole, time behaves in a way that depends strongly on perspective. For a distant observer, a clock falling toward the event horizon appears to slow down more and more. The light signals from that clock take increasingly long to reach the observer. The clock never appears to cross the horizon. It seems to freeze just outside it. From the perspective of the falling clock, however, time proceeds normally. Nothing special happens at the horizon itself. The clock continues ticking. The person carrying it experiences no sudden halt in time. This contrast is not a contradiction. It reflects the fact that time comparisons between regions of strongly curved space-time are deeply frame-dependent. The key point is that time near a black hole is not globally defined. There is no single time coordinate that smoothly covers both the region far away and the region near the horizon in a way that all observers can agree on. Different coordinate choices emphasize different aspects of the geometry. This breakdown of a universal time coordinate is not a mathematical inconvenience. It is a reflection of physical reality. Near extreme objects, the structure of space-time does not support a single, shared notion of time. The situation becomes even more striking when considering the interior of a black hole. According to general relativity, once an object crosses the event horizon, all future paths lead inevitably toward the singularity at the centre. Inside the horizon, the roles of space and time effectively swap in a precise mathematical sense. The singularity lies in the future, not in a direction through space. This statement is not metaphorical. It means that moving toward the singularity is as unavoidable as moving toward tomorrow. There is no way to remain at a fixed distance from the singularity, just as there is no way to remain at a fixed time. Time itself, as experienced by any object inside, is directed toward that endpoint. Here, time behaves not just differently, but fundamentally differently from the outside universe. The structure of space-time enforces a temporal direction that cannot be escaped. This is not a property of motion or choice. It is a property of geometry. Extreme behavior of time is not limited to black holes. The early universe presents another example. Shortly after the Big Bang, the universe was extraordinarily dense and hot. Energy densities were immense. Space-time curvature was extreme everywhere, not just near isolated objects. In that early environment, the familiar separation between space and time loses clarity. Expansion rates were enormous. Timescales were short. Processes unfolded under conditions that no longer resemble anything in the present universe. Cosmological models describe this early phase using space-time geometry that evolves rapidly. Time in these models is closely tied to the expansion of space itself. Asking what time was like before the Big Bang becomes problematic, because the concept of time is bound up with the existence of space-time. In these regimes, the idea of time as something flowing independently becomes untenable. Time is part of the evolving geometry. It cannot be extracted and examined in isolation. Another class of extreme objects involves regions with intense energy flux, such as those near rapidly rotating massive bodies, or within powerful gravitational waves. In these situations, space-time curvature changes dynamically. Time does not just slow uniformly, it fluctuates depending on local conditions. Gravitational waves, ripples in space-time produced by accelerating masses, carry energy that distorts space-time as they pass. As a gravitational wave moves through a region, it stretches and compresses space-time. This includes the temporal dimension. Clocks separated by distance experience tiny changes in their ticking rates as the wave passes. These effects are extremely small, but they have been measured indirectly through precise instruments designed to detect gravitational waves. Once again, time reveals itself as responsive to space-time dynamics. What unites all these examples is not drama or violence, but curvature. Extreme objects create extreme curvature. Extreme curvature alters the geometry of space-time. Altered geometry changes how time accumulates. This geometric explanation avoids invoking mysterious forces acting on time. Nothing pushes time or pulls it. Time behaves differently because the space-time paths along which clocks move have different lengths. This perspective also clarifies why extreme time behavior does not violate causality. Even near black holes, cause and effect remain well defined along world lines. Signals cannot propagate backward in time. The structure of space-time ensures consistency, even when intuition struggles. One might ask whether time actually slows near extreme objects, or whether this is merely an appearance caused by signal delays and coordinate choices. The answer is subtle. Locally, time always feels normal. Any clock measures its own proper time without noticing distortion. The slowing is revealed only through comparison between regions. This does not make the effect any less real. Physics is built on comparisons. If two clocks disagree after being reunited, something physical has occurred. The difference in accumulated time reflects the structure of space-time they traversed. Extreme objects magnify this difference until it becomes impossible to ignore. They turn what was a theoretical curiosity into a dominant feature. At this point, it becomes difficult to maintain any notion of time as a universal background. Time does not merely vary slightly. It fractures into locally defined measures that depend on geometry. In regions of extreme curvature, even defining a global time coordinate becomes impossible. This realization has consequences for attempts to unify general relativity with quantum mechanics. Quantum theory relies heavily on a fixed background time parameter. In extreme gravitational environments, such a parameter may not exist. Time itself becomes ambiguous. This ambiguity is not a failure of mathematics. It is a reflection of the physical situation. Extreme objects push space-time to its limits, exposing the assumptions hidden in simpler models. It's also worth noting that extreme time behavior is not confined to exotic astrophysical objects. Any sufficiently concentrated energy density would produce similar effects. The universe does not reserve these behaviors for special cases. They're inherent in the structure of space-time. From a broader perspective, extreme objects serve as laboratories. They reveal how time behaves when stripped of the approximations that make it seem simple. They show that time is not an independent ingredient added to the universe, but an expression of its geometry. As understanding deepens, the question naturally arises whether time itself is fundamental, or whether it emerges from something deeper. Extreme environments challenge the idea that time is always well defined. In some regimes, time appears to dissolve into a coordinate choice rather than a physical quantity. These questions cannot be answered yet. They sit at the frontier of physics, where general relativity and quantum mechanics intersect. But the behavior of time near extreme objects provides important clues. It suggests that time is not absolute, not universal, and not guaranteed to exist in the same form everywhere. It is contextual, shaped by mass, energy, and geometry. Thus far, the focus has been on how fast time passes. Another mystery remains. Why does time seem to move in one direction at all? Even in a universe where time bends and slows, it still appears to have an arrow. Once time is no longer treated as a rigid backdrop, another question quietly becomes unavoidable. If time can slow, stretch, and behave differently depending on motion and gravity, then why does it still seem to move in only one direction? No matter where you are or how fast you travel, your memories point backward. Causes precede effects. Glasses shatter, but they do not spontaneously reassemble. Heat flows from hot objects to cooler ones, never the other way around. Even when time bends near extreme objects, it still appears to have a direction. This direction is what physicists call the arrow of time. At first glance, this might seem like a psychological issue rather than a physical one. After all, our experience of time's direction is deeply tied to memory, expectation, and biological processes. But physics takes the question seriously, because at a fundamental level, most physical laws do not prefer one direction of time over the other. The equations describing motion, electromagnetism, and even much of quantum mechanics work just as well if time runs backward. This creates a tension. The laws governing the universe appear time-symmetric, yet the universe we observe is not. Somewhere between fundamental equations and everyday experience, a direction emerges. The key to resolving this tension lies not in time itself, but in entropy. Entropy is a concept from thermodynamics, and while it is often loosely described as disorder, that description is incomplete. More precisely, entropy measures how many microscopic configurations correspond to a macroscopic state. It counts how many ways a system can be arranged internally while appearing the same from the outside. Consider a simple example. Imagine a box divided into two halves, with all the gas molecules initially confined to one side. This is a low entropy state because there are relatively few ways to arrange all molecules in just one half of the box. Remove the divider and the gas spreads out to fill the entire box. This new state has much higher entropy because there are vastly more ways for the molecules to be distributed throughout the whole volume. The laws of physics do not forbid the gas from spontaneously gathering back into one half of the box. That configuration is allowed by the equations of motion. What makes it effectively impossible is probability. The number of microstates corresponding to the evenly spread gas is astronomically larger than the number corresponding to the compressed gas. The system almost certainly evolves toward higher entropy, simply because there are more ways for it to be that way. This statistical tendency gives rise to the arrow of time. The direction we call forward is the direction in which entropy increases. The direction we call backward is the direction in which entropy decreases. The universe overwhelmingly prefers the former. What is important here is that the arrow of time is not built into the fundamental laws. It emerges from the behaviour of large collections of particles under particular conditions. Time itself does not push systems toward disorder. Instead, systems naturally move from less probable states to more probable ones. This distinction matters. It means that the arrow of time is not a property of time in isolation. It is a property of how matter and energy are arranged and how they evolve statistically. To see how deeply this affects everyday experience, consider memory. Memories are physical records stored in the brain. Forming a memory requires energy and increases entropy. You can remember the past because physical processes have left traces of it. You cannot remember the future because those traces do not yet exist. This asymmetry is not imposed by time. It arises from the thermodynamic cost of recording information. The same logic applies to causality. Causes precede effects because effects typically involve the dispersal of energy and the increase of entropy. A light bulb turns on after a switch is flipped, not before, because flipping the switch initiates processes that spread energy outward. Reversing that sequence would require an improbable concentration of energy and information. This connection between entropy and temporal direction explains why time's arrow aligns across so many domains. The psychological arrow, the causal arrow, and the thermodynamic arrow all point in the same direction, because they are rooted in the same statistical behaviour of matter. What makes this particularly intriguing is that entropy increase depends on initial conditions. For entropy to increase, the universe must start in a state of relatively low entropy. And this raises a profound question. Why did the universe begin in such an ordered state? The early universe, shortly after the Big Bang, was hot and dense, but it was also remarkably uniform. Matter and energy were distributed almost evenly. From a gravitational perspective, this uniformity represents a low entropy state. Over time, gravity caused matter to clump, forming stars, galaxies, and eventually complex structures. Entropy increased. This initial low entropy condition is not explained by the known laws of physics. It is an observed fact about the universe. The arrow of time, therefore, is not something that arises automatically from physical laws alone. It depends critically on how the universe began. This dependence is unsettling because it suggests that the direction of time is contingent rather than fundamental. If the universe had begun in a high entropy state, there might be no arrow of time at all. Processes would still occur, but there would be no clear distinction between past and future. Some physicists have suggested that the arrow of time is an emergent feature that exists only because of this special beginning. Others have proposed that deeper laws might explain why low-entropy initial conditions are natural or inevitable. So far, no consensus exists. What is clear is that entropy provides a unifying explanation for why time appears directional, despite the time-symmetric nature of fundamental laws. The arrow of time is not written into the equations. It emerges from the statistics of large systems evolving from special initial conditions. This perspective also helps clarify why time dilation and gravitational effects do not reverse the arrow of time. Even near black holes, where time behaves strangely, entropy still increases along world lines. Processes still unfold in a direction consistent with increasing disorder. The geometry of space-time may distort the rate of time's passage, but it does not reverse the statistical tendency underlying entropy. There is one subtle exception worth mentioning. Certain interactions in particle physics violate time reversal symmetry at a very small scale. These violations are real, but they are extremely weak, and do not explain the macroscopic arrow of time we experience. The dominant source of time's direction remains thermodynamic. Understanding the arrow of time as a consequence of entropy also reframes familiar experiences. Aging, decay, and irreversibility are not failures of symmetry. They are expressions of probability. Living systems maintain local order by exporting entropy to their surroundings. Life itself depends on this imbalance. From this point of view, the flow of time is inseparable from the flow of energy. Where energy spreads out, time appears to move forward. Where energy is constrained, process is slow. Time's arrow follows the path of increasing entropy through space-time. This insight does not make time less real. It makes it more contextual. Time's direction is not an independent rule imposed on the universe. It is a pattern that arises from how the universe is arranged and how it evolves. As this understanding settles in, it naturally leads to another question. If the arrow of time emerges from entropy, and entropy depends on how systems are arranged, then why do the fundamental laws themselves seem indifferent to time's direction? Why do they allow both forward and backward evolution? Look closely at the equations that govern physics, and something unexpected begins to stand out. Despite everything we experience about time moving forward, despite aging, decay, memory, and entropy, most of the fundamental laws do not seem to care which way time points. Write them down, reverse the direction of time in the mathematics, and in many cases nothing breaks. The equations remain valid. The universe, at least on paper, appears just as comfortable running backward as it does running forward. This indifference is deeply unsettling when placed alongside lived experience. Every human intuition insists that time has a direction. You remember yesterday, not tomorrow. You spill milk and it spreads, but it does not leap back into the glass. You watch smoke disperse into the air, never the reverse. Yet the mathematical rules describing particles, forces, and fields mostly refuse to acknowledge this preference. Physics, at its core, seems strangely unconcerned with the arrow of time. To understand why this is the case, it helps to separate two ideas that are often blended together. One is the behavior of physical laws themselves. The other is the behavior of physical systems composed of many particles. These are not the same thing, even though they are closely related. Start with classical mechanics, the framework developed by Newton. The equations describing motion under forces are time reversal symmetric. If you take a solution to Newton's equations and replace time with its negative, the result is still a valid solution. A ball rolling down a hill follows the equations just as well as a ball rolling up the same hill, provided the forces are reversed accordingly. The equations do not forbid motion in either temporal direction. They do not encode friction, wear, or irreversibility at the fundamental level. Those features emerge only when additional assumptions are added, such as energy dissipation into microscopic degrees of freedom. This symmetry is not limited to mechanics. Maxwell's equations, which describe electromagnetism, are also largely time reversal symmetric. Electric and magnetic fields evolve according to equations that do not inherently distinguish past from future. If you reverse the motion of charges and fields appropriately, the equations remain valid. Even quantum mechanics, which introduces probabilities and uncertainties, largely preserves this indifference. The Schrödinger equation evolves quantum states in time, but it does so in a way that is symmetric under time reversal when properly formulated. The fundamental evolution does not select a preferred direction. This raises an obvious question. If the laws are symmetric, why is the world not? Why does reality not routinely display reverse processes? Why do we not see shattered objects reassemble or heat flow from cold to hot? The answer lies not in the laws themselves, but in the conditions under which those laws operate. Physical laws describe what is allowed. They do not dictate what is likely. Probability enters when many degrees of freedom are involved. Entropy is the bridge between time-symmetric laws and time-asymmetric experience. As discussed earlier, entropy measures how many microscopic configurations correspond to a macroscopic state. Systems naturally evolve from less probable states to more probable ones, simply because there are vastly more ways to be disordered than ordered. The laws permit entropy to decrease, they do not forbid it. But the probability of spontaneous entropy decrease in large systems is so small that it never occurs in practice. This statistical asymmetry gives rise to the arrow of time, even though the laws themselves remain neutral. An analogy can help clarify this point. Consider a perfectly fair coin. The laws governing its behavior are symmetric. heads and tails are equally allowed. Yet if you flip the coin a million times, you will almost certainly see roughly equal numbers of heads and tails, not a million heads in a row. The laws do not forbid the latter outcome. Probability makes it effectively impossible. Similarly, the laws of physics do not forbid entropy decrease. Probability makes it overwhelmingly unlikely in macroscopic systems. This distinction explains why reversing a video of microscopic particle interactions often looks plausible, while reversing a video of everyday events does not. At small scales, where few particles are involved, entropy changes are modest and reversals are not absurdly improbable. At large scales, the number of particles involved makes reversal astronomically unlikely. Another important factor is that the fundamental laws describe local interactions. They govern how particles influence one another in immediate proximity. The arrow of time, by contrast, is a global property that emerges when many such interactions are considered together over extended regions of space-time. Local laws do not encode global direction. They operate moment to moment, interaction to interaction. Directionality arises only when the initial conditions constrain how those interactions unfold statistically. This helps explain why physical laws mostly ignore time's direction. They were never meant to encode it. Direction is not a primitive feature at the level of individual interactions. It is an emergent feature of complex systems evolving from special initial states. There is, however, a small but important caveat. Certain processes in particle physics do violate time reversal symmetry in a strict sense. These violations are associated with weak nuclear interactions and are observed in the behavior of certain subatomic particles such as kaons and B-mesons. In these systems, the probability of a process occurring forward in time is not exactly the same as the probability of the time-reversed process. This is genuine time reversal violation, not merely a statistical effect. However, these violations are extremely subtle. They occur only in rare processes under specific conditions. More importantly, they do not explain the macroscopic arrow of time. Their effect is far too small to account for everyday irreversibility. As a result, most physicists agree that while time reversal violation exists at a fundamental level, it is not the primary source of time's arrow as we experience it. The dominant contributor remains entropy and initial conditions. This brings attention back to the early universe. For entropy to increase, the universe must have started in a state of unusually low entropy. This fact is not explained by time's symmetric laws alone. It is an additional condition imposed on the universe's history. The laws describe how the universe evolves given a starting point. They do not specify that starting point. The arrow of time, therefore, reflects not just the laws, but the universe's initial configuration. This has deep implications. It suggests that the direction of time is contingent rather than fundamental. If the universe had begun differently, the arrow of time might not exist at all, or might exist in a different form. Some speculative models even consider universes in which entropy decreases in one temporal direction away from a low entropy boundary, creating two arrows pointing in opposite directions. In such models, what one region calls the future, another might call the past. These ideas remain theoretical, but they illustrate how tightly time's direction is linked to boundary conditions rather than laws. Another reason physical laws ignore time's direction is practical. Physics seeks universal principles that apply under all conditions. Encoding a preferred direction of time into the laws would require specifying special states or histories, which would undermine their generality. Instead, physics separates dynamics from conditions. The laws provide the rules. The universe's initial state determines how those rules play out. This division allows the same laws to describe vastly different scenarios without modification. There is also a deeper conceptual reason. At the most fundamental level, physics is concerned with relations between events, not with an evolving present. The equations describe how states relate to one another across space-time, not how the universe moves through time. This perspective becomes especially clear in relativistic physics. where space-time is treated as a four-dimensional structure. The laws describe relationships within that structure. They do not single out a preferred direction along the time dimension. From this viewpoint, asking why the laws ignore time's direction is a bit like asking why the laws ignore north versus south. Directions exist within the structure, but the structure itself does not privilege one over the other. Time's arrow emerges only when additional information is supplied, namely the universe's boundary conditions and the presence of large numbers of degrees of freedom. This way of thinking also helps clarify why time feels directional to conscious observers. Brains are physical systems that operate far from equilibrium. They maintain order by exporting entropy. Memory formation, perception, and decision-making all rely on irreversible processes. Conscious experience, therefore, inherits the arrow of time from thermodynamics. We experience time flowing forward because our physical structure depends on entropy increase. The laws themselves do not need to encode this experience. They only need to allow systems like brains to exist under certain conditions. The directionality then arises naturally. This separation between laws and experience can feel unsatisfying, as though physics is evading the question. But it reflects a broader pattern in science. Many features of reality that feel fundamental turn out to be emergent. Temperature, for example, is not a property of individual particles. It emerges from collective behaviour. Pressure, viscosity, and sound are similar. Time's arrow appears to belong in this category. Understanding this does not diminish the reality of time's direction. Emergent phenomena are no less real for being emergent. They are simply not fundamental. The fact that physical laws mostly ignore time's direction also opens the door to new ways of thinking about time itself. If the laws do not require a flowing time, perhaps time is not a fundamental ingredient of the universe, but a useful parameter that emerges under certain conditions. This idea becomes more compelling when considering attempts to unify general relativity and quantum mechanics. In some approaches to quantum gravity, time does not appear in the fundamental equations at all. The universe is described in a timeless way, with change emerging relationally. Such approaches remain incomplete, but they reflect a growing recognition that time may not occupy the role we once assigned it. For now, what can be said with confidence is this: physical laws mostly ignore time's direction because direction is not their job. They describe allowed relationships, not preferred histories. The arrow of time arises from how those relationships are instantiated in a particular universe with particular initial conditions. This perspective does not make time an illusion. It makes time contextual. Directionality depends on scale, complexity, and boundary conditions. Another question naturally comes into focus. If the laws themselves are indifferent to time's direction, and if time's arrow emerges only under certain conditions, what happens at scales where those conditions break down? What happens when quantum effects dominate, or when gravity and quantum mechanics must be combined? Set aside for a moment everything that feels familiar about clocks and calendars, because quantum mechanics approaches time in a way that is quietly unsettling. Not dramatic, not loudly paradoxical, but subtly incompatible with almost everything discussed so far. After relativity reshaped time into something flexible, local, and woven into space-time, one might expect quantum mechanics to continue in that direction. Instead, it does something far stranger. It mostly refuses to talk about time at all. Quantum mechanics is the most successful physical theory ever devised when it comes to predicting experimental outcomes. It describes atoms, electrons, photons, chemical bonds, semiconductors, lasers, and the behavior of matter at the smallest scales we can probe. And yet, within its formal structure, time occupies an oddly passive role. It is not treated as a physical quantity on the same footing as position, momentum, or energy. It does not fluctuate. It does not become uncertain. It does not respond to measurement. It simply sits in the equations, assumed rather than explained. This is not a philosophical oversight, it is a structural feature of the theory. In standard quantum mechanics, the central equation governing how systems evolve is the Schrödinger equation. This equation tells you how the quantum state of a system changes with time, but time itself is not represented by an operator. There is no time observable in the same sense that there is an observable for position or momentum. You cannot ask a quantum system what time it is in the same way you can ask where it is or how fast it is moving. Instead, time appears as an external parameter, something classical, something assumed to exist outside the quantum system being described. The quantum state evolves with respect to time, but time is not part of the quantum state. This immediately creates tension with relativity. In relativity, time is not external. It is part of space-time. It is dynamical. It is shaped by motion and gravity. There is no universal time parameter that applies everywhere. Each observer carries their own time. Quantum mechanics, by contrast, quietly assumes a single background time against which all quantum evolution unfolds. This time is absolute, in a way that looks uncomfortably similar to Newton's time. It ticks uniformly. It does not bend. It does not slow near mass. It does not care about observers. For a theory that otherwise revolutionized physics, this conservatism about time is striking. The puzzle deepens when measurement enters the picture. Quantum systems evolve smoothly and deterministically according to the Schrödinger equation until a measurement is made. At that point, the system appears to undergo a sudden change, often described as wave function collapse. This collapse is not described by the same time evolution equation. It is instantaneous, or at least not governed by a clear dynamical rule. This raises uncomfortable questions. When does collapse happen? In what time frame? Relative to which observer? If time is merely a parameter, how does a fundamentally probabilistic event suddenly become definite at a particular moment? Different interpretations of quantum mechanics answer these questions differently, but none remove the underlying tension. Time is treated inconsistently. Smooth evolution on one hand, sudden change on the other, all reference to an external clock that the theory itself does not explain. Even more unsettling is the role of time in quantum uncertainty. Position and momentum are linked by the uncertainty principle. Energy and time are often said to be linked in a similar way, but this analogy is misleading. The energy-time uncertainty relation does not arise from non-commuting operators in the same way. It reflects limits on how precisely energy can be defined over a finite duration, not uncertainty in time itself. Time, again, remains outside the system. This means that quantum mechanics allows uncertainty in many quantities, but not in time. Time does not become fuzzy or probabilistic. It remains sharp, classical, and assumed. At first, this might seem harmless. After all, quantum mechanics works exceptionally well. Why worry about how it treats time if it produces correct predictions? The issue becomes unavoidable when gravity enters the picture. Gravity, according to general relativity, is geometry. It makes space-time dynamic. Time itself responds to mass and energy. There is no fixed background time in a gravitational universe. Trying to combine quantum mechanics, which assumes a fixed time parameter, with general relativity, which denies such a thing, leads to deep conceptual problems. This conflict is known as the problem of time. The problem of time is not a single technical issue. It is a collection of related difficulties that arise whenever one tries to describe the universe quantum mechanically as a whole. In quantum mechanics, systems evolve with respect to time. But if the entire universe is treated as a quantum system, what time does it evolve with respect to? There is nothing outside the universe to supply an external clock. This is not a philosophical quibble. It shows up mathematically. When physicists attempt to write down an equation describing the quantum state of the entire universe, time often disappears entirely. One such equation is the Wheeler-DeWitt equation, which arises in certain approaches to quantum gravity. Unlike the Schrödinger equation, the Wheeler-DeWitt equation does not contain a time variable at all. The quantum state of the universe appears static. There is no explicit time evolution. This result is deeply unsettling. It suggests that, at a fundamental level, the universe may be timeless. Change, motion, and evolution would then have to emerge in some indirect way. If taken literally, this would mean that time is not a fundamental feature of reality, but an emergent one. It would arise only when certain conditions are met, such as when subsystems of the universe interact and serve as clocks for one another. Several approaches attempt to make sense of this idea. One common strategy is to treat time relationally. Instead of evolving with respect to an external parameter, systems evolve with respect to one another. One part of the system acts as a clock, and other parts are described in relation to it. In this view, time is not something that exists independently. It is something that arises from correlations between physical systems. A clock does not measure time, it defines it. This idea aligns surprisingly well with earlier insights. We never measure time directly, we measure change. Clocks track repetitive physical processes. If those processes are treated quantum mechanically, then time itself becomes a property of relationships rather than a background structure. However, implementing this idea consistently is difficult. Quantum systems do not always behave like good clocks. They fluctuate, they become entangled, they decohere. Defining a clean temporal ordering becomes challenging. Another approach is to treat time as emergent from quantum entanglement. Some theories suggest that the growth of entanglement between subsystems could define a direction and sense of time. As systems become more entangled, information spreads, and something like temporal ordering emerges. This is still speculative, but it reflects a broader shift in thinking. Time may not be fundamental. It may be a byproduct of quantum correlations in a complex universe. There is also the many-worlds interpretation, which eliminates wave function collapse entirely. In this picture, the quantum state always evolves smoothly according to the Schrödinger equation. Measurement does not cause collapse. Instead, the universe branches into multiple non-interacting outcomes. Time in this interpretation is still treated as a parameter, but the puzzle of collapse timing disappears. However, the deeper problem remains. Time is still assumed, not explained. Across all interpretations, quantum mechanics treats time differently from other physical quantities. It is not quantized, it is not dynamic, it does not fluctuate, it does not interact. This asymmetry becomes especially troubling when compared to relativity, where space and time are treated symmetrically. Space can stretch, time can stretch, space can curve, time can curve. In quantum mechanics, space becomes uncertain, discrete, and operator valued. Time does not. This mismatch is not cosmetic. It blocks attempts to unify the theories. Another clue that quantum mechanics does not fully understand time comes from quantum tunneling. In tunneling, particles appear to cross barriers faster than expected. Defining how long tunneling takes is surprisingly difficult. Different definitions of tunneling time lead to different answers. Some suggest zero time, others suggest complex valued times. This is not because experiments are flawed, it is because quantum mechanics lacks a clear notion of time duration for certain processes. Time is not an observable, so durations become ambiguous. Similar issues arise in decay processes. A particle decays probabilistically. There is a characteristic lifetime, but the exact moment of decay is unpredictable. Time plays a statistical role, not a deterministic one. All of this suggests that quantum mechanics uses time instrumentally rather than fundamentally. Time is a parameter that allows calculations to proceed, but the theory does not explain where it comes from, or why it behaves the way it does. This is deeply different from relativity, where time is central and physical. The puzzle, then, is not simply that quantum mechanics treats time strangely. It is that it treats time in a way that appears incompatible with our best theory of space-time. And yet, both theories are extraordinarily successful in their respective domains. Quantum mechanics works at small scales. General relativity works at large scales. Time behaves differently in each framework, and neither seems willing to give way easily. This situation strongly suggests that our current understanding of time is incomplete. Neither theory alone captures the full picture. Time may look classical in one context, geometric in another, and relational in a third. What this means for the nature of time remains an open question. It may be that time is not a single thing, but a layered concept that behaves differently depending on scale and context. At everyday scales, time feels absolute. At relativistic scales, it bends and stretches. At quantum scales, it recedes into the background, barely acknowledged. Rather than being contradictory, these perspectives may be complementary. Each captures an aspect of time relevant to a particular regime. Remove time from the equations, and physics begins to feel unrecognizable. Not because the mathematics collapses, but because intuition does. After everything learned about time slowing with motion, bending with gravity, and quietly directing experience through entropy, the idea that time might vanish entirely from fundamental equations sounds like a mistake. And yet, in some of the most serious attempts to describe reality at its deepest level, that is exactly what happens. Time does not bend. It does not slow. It is simply not there. This is not a rhetorical claim. It is a concrete result that appears when physicists try to combine quantum mechanics with general relativity. Each theory, taken on its own, treats time in a very different way. When they are forced into the same mathematical framework, neither treatment survives intact. What emerges instead is something far stranger, a description of the universe that does not evolve in time at all. To see why this happens, it helps to recall how time enters physics in the first place. In classical mechanics, time is an external parameter. Systems evolve with respect to it. In quantum mechanics, time remains external, even as everything else becomes probabilistic. In general relativity, time becomes part of space-time and responds dynamically to mass and energy. Already, these views are in tension. The conflict becomes unavoidable when attempting to describe the universe itself as a quantum system. Quantum mechanics assumes an external clock. But if the universe includes everything, there is nothing outside it to provide that clock. Time cannot be borrowed from elsewhere. It must either be internal to the universe or not appear at all. When physicists attempt to quantize general relativity, this problem surfaces immediately. One of the simplest formulations leads to an equation intended to describe the quantum state of the entire universe. This equation, known as the Wheeler-DeWitt equation, has an unsettling feature. There is no time variable in it. The equation does not say that the universe evolves slowly or quickly. It does not describe evolution at all. It presents the universe as a static object, defined by constraints rather than by change. From the perspective of the equation, nothing happens. This result is often referred to as the frozen formalism. It is not that the universe is literally frozen in a physical sense. It is that the mathematical description contains no parameter corresponding to time evolution. The familiar idea of states changing moment by moment is absent. At first, this looks like a failure. How can a timeless equation describe a universe full of motion, processes, and events? How can stars form, atoms vibrate, and thoughts unfold if the fundamental description is static? The discomfort arises because everyday experience is saturated with change. We equate change with time so deeply that removing time feels like removing reality itself. But physics is not obligated to preserve intuition. It is obligated to describe what measurements and principles demand. The absence of time in these equations is not accidental. It reflects the fact that general relativity treats time as a coordinate that can be chosen in different ways. There is no preferred time coordinate built into the theory. When the theory is quantized, that flexibility becomes a constraint. Time loses its special status. In general relativity, different choices of time correspond to different ways of slicing space-time into spatial sections. None of these choices is physically privileged. The laws remain the same. When this symmetry is carried into the quantum description, it eliminates the possibility of a unique time variable. What remains are relationships between configurations. The universe is described by correlations between different degrees of freedom, not by evolution with respect to an external clock. This shift is subtle, but profound. Instead of asking how a system changes over time, the question becomes how different aspects of the system are related. Change becomes relational rather than temporal. To make this idea more concrete, imagine a very simple universe containing only two physical quantities. Instead of asking how one quantity changes over time, one can ask how one quantity changes relative to the other. One variable can serve as a reference against which the other varies. In this picture, time is not fundamental. It is an emergent bookkeeping device that arises when one part of a system is used as a clock for another part. The clock does not measure time, it defines it. This relational approach to time appears in several attempts to address the problem. One version involves identifying a physical degree of freedom that behaves monotonically and using it as an internal time parameter. Other degrees of freedom are then described as evolving relative to it. While this can restore a sense of change, it is not a complete solution. Different choices of internal clocks can lead to different descriptions. There is no unique time. Time becomes contextual. This contextuality aligns with earlier insights from relativity. Different observers carry different times. There is no universal present. The disappearance of time from fundamental equations pushes this idea to its logical extreme. Another approach involves quantum entanglement. In some models, time emerges from correlations between subsystems. As entanglement spreads, information flows, and an effective temporal ordering arises. In these models, time is not a background parameter, but a pattern in the structure of quantum correlations. Change is encoded in how subsystems relate to one another, not in an external ticking variable. This idea has gained traction because it resonates with how time is actually measured. Clocks are physical systems. They interact with other systems, they become entangled with their environments. Their readings are not abstract numbers, they are physical states. If clocks are quantum systems, then time itself may be inseparable from quantum relationships. The disappearance of time from equations also sheds light on the arrow of time. If the fundamental description is timeless, then directionality cannot be fundamental. It must emerge from asymmetries and correlations, initial conditions, or entanglement patterns. This fits naturally with the thermodynamic arrow. Entropy increased describes how correlations spread, and information becomes less accessible. The direction of time may correspond to the direction in which correlations grow. From this perspective, the flow of time is not a feature of the universe as a whole, but a feature of subsystems embedded within it. Observers experience time because they are physical systems interacting irreversibly with their surroundings. The universe itself, described as a whole, may not need time. This idea challenges deeply held assumptions. It suggests that the universe does not evolve in time. Instead, time is something that exists only within the universe, not for the universe. This is difficult to accept because language itself is temporal. Even describing a timeless universe requires temporal phrasing. But the mathematical structures do not share this limitation. Importantly, a timeless description does not imply that change is illusory. It implies that change is encoded statically, in relationships rather than in motion through time. Consider a book. The entire story exists at once in the printed pages. Characters move, events unfold, causes lead to effects. But the book itself does not change. The progression of the story is experienced by a reader, not by the book. This analogy is imperfect, but it captures something essential. A timeless structure can encode dynamic experiences without itself evolving. In space-time physics, a similar idea appears in the block universe picture. All events exist within space-time. Change is represented by relations between events, not by a moving present. When time disappears from equations, this block-like description becomes unavoidable. The universe is described as a whole, not as something unfolding. This raises difficult questions about causality and agency. If the universe is timeless at the fundamental level, what does it mean to cause something? What does it mean to choose? Physics does not answer these questions directly. It describes structure, not meaning. But it does suggest that causality, like time's arrow, may be emergent rather than fundamental. Another implication concerns measurement. In a timeless universe, measurement cannot be an event that happens at a particular time in an absolute sense. It must be described relationally, as a correlation between system and apparatus. This aligns with modern approaches to quantum measurement, which emphasize decoherence and entanglement rather than instantaneous collapse. Measurement becomes a process embedded in a network of correlations. Seen this way, the disappearance of time from equations is not a failure of physics. It is a clue. It suggests that time is not the foundation upon which reality is built. It is something that arises within reality under certain conditions. This does not mean that time is unreal. Emergent phenomena are no less real for being emergent. Temperature is real. Pressure is real. Life is real. None of these appear in the fundamental equations of particle physics. Time may belong in the same category. The challenge is that time feels more fundamental than these other quantities. It frames all experience. But feeling fundamental is not the same as being fundamental. Physics has repeatedly shown that intuition is shaped by scale. What feels basic at one scale dissolves at another. Solidity dissolves into atoms. Continuous motion dissolves into quantum jumps. Absolute time may dissolve into relational structure. At present, there is no complete theory that fully explains how time emerges from a timeless foundation. Different approaches offer partial insights. None has been confirmed experimentally. What is clear is that attempts to unify physics consistently push time out of its traditional role. Whether through quantum gravity, relational dynamics, or entanglement-based models, time becomes less central, not more. This trend suggests that asking what time is may require reframing the question. Instead of asking what time does, one might ask under what conditions time appears at all. Those conditions seem to involve complexity, interaction, and irreversibility. Where systems exchange information, form records, and increase entropy, time emerges as a useful parameter. Where those conditions fail, time fades from the description. This brings the exploration to a delicate point. If time can disappear from the equations describing the universe as a whole, then time may not be a universal feature of reality. It may be local, contextual, and emergent. Understanding this does not eliminate mystery, it deepens it. The disappearance of time does not close the question, it opens a new one. If time is not fundamental, then what is? And how does something as pervasive as temporal experience arise from something that does not include time at all? Begin instead with a question that physics did not always think it needed to ask. When we say that something exists, what do we actually mean? Is existence reserved for things that appear explicitly in fundamental equations? Or can something be just as real while arising only under certain conditions? Temperature, pressure, sound, and even solidity do not appear in the most basic equations of particle physics, yet no one doubts their reality. Against that background, the question of whether time is fundamental or emergent stops sounding abstract and starts sounding unavoidable. For centuries, time was treated as fundamental by default. It did not need justification because it seemed to frame everything else. Motion happened in time. Change happened in time. Causes preceded effects in time. Even when relativity complicated time, bending and stretching it, time itself still appeared as a basic ingredient of space-time. But the moment quantum gravity enters the discussion, that certainty begins to erode. Time starts to behave less like a foundation and more like a consequence. To clarify what is at stake, it helps to define what physicists usually mean by fundamental. A fundamental entity is one that cannot be derived from something else. It does not depend on scale, approximation, or collective behaviour. It is present in the deepest description available. By contrast, an emergent entity arises only when many components interact in particular ways. It is real, measurable, and often indispensable, but it is not basic. Sound is a useful comparison. At the level of individual air molecules, there is no sound. There are only particles colliding and moving. Sound emerges when those motions organize into waves that propagate through matter. Remove the medium, and sound disappears. The laws governing molecules remain, but sound does not. The same is true of temperature. A single particle does not have a temperature. Temperature emerges only when many particles exchange energy. It becomes meaningful only statistically. Yet temperature is indispensable for describing thermodynamics, chemistry, and life itself. The question, then, is whether time resembles space, mass, and charge, or whether it resembles temperature and pressure. Does it exist at all scales as a primitive feature of reality, or does it arise only when certain conditions are met? Relativity initially suggested that time was fundamental but flexible. It merged time with space into space-time, treating both as geometric aspects of the universe. Time could slow, stretch, and curve, but it was still there, embedded in the fabric. Quantum mechanics complicated this picture by treating time differently from every other quantity. Space became an operator. Energy became quantized. Fields fluctuated. Time remained external, classical, and untouched. That inconsistency was tolerable as long as gravity was ignored. The moment gravity is included at the quantum level, time begins to vanish from the equations. This is not a philosophical choice. It is a mathematical outcome. The most direct attempts to quantize gravity lead to descriptions in which there is no time parameter governing evolution. This is the strongest evidence physics currently has that time may not be fundamental. Fundamental equations do not usually discard foundational concepts casually. When something drops out entirely, it demands attention. Still, disappearance alone does not settle the issue. It could mean the formulation is incomplete. It could mean time is hidden in a different form, or it could mean time truly emerges only under certain conditions. To explore that possibility, consider how time is actually used in practice. We never observe time directly. We observe processes. We compare change against change. A clock does not detect time as a substance. It tracks a repeating physical process and uses it as a reference. Every operational definition of time relies on correlation. One thing changes while another thing changes, and their relationship is labelled temporal. This is already suggestive. If time were fundamental in the same way as mass or charge, one might expect it to be directly measurable, not inferred. This relational character becomes even more apparent in relativistic physics. Different observers carry different times. There is no universal clock. Time becomes local. It belongs to world lines, not to the universe as a whole. If time were truly fundamental, one might expect it to be global. Instead, it fragments. The emergent view takes this fragmentation seriously. It suggests that time arises when systems are complex enough to serve as clocks for one another. In this picture, time is not something the universe contains. It is something subsystems within the universe create through interaction. One version of this idea treats time as emerging from correlations. Suppose a large system contains many interacting parts. If one subset of those parts behaves in a regular, monotonic way, other parts can use it as a reference. That reference defines time internally. Crucially, different choices of reference lead to different times. There is no unique temporal parameter. Time becomes contextual. This sounds strange, but it mirrors how time already works in relativity. Observers in different states of motion define time differently. The emergent picture simply removes the last assumption of a hidden universal time underneath. Another line of thought connects time's emergence to entropy and information. As systems interact, information spreads, records form, correlations become inaccessible. This irreversible spreading defines an arrow. Where there is an arrow, there is an effective time. In this view, time emerges wherever entropy increases. Systems far from equilibrium experience time because they are embedded in irreversible processes. Near equilibrium, time loses meaning. This idea explains why time feels vivid to living systems. Life operates far from equilibrium. It maintains order by exporting entropy. Memory formation, perception, and learning all rely on irreversible processes. Time is woven into biology because biology depends on thermodynamics. The universe as a whole, by contrast, may not need time. It may simply contain a vast network of correlations within which local arrows arise. There is also a geometric version of emergence. In space-time physics, one can describe the universe as a four-dimensional structure containing all events. Nothing moves or flows globally. Instead, change is represented by relationships between events. Observers experience time because their world lines cut through this structure in particular ways. Past and future are not global properties. They are local orientations within space-time. In this sense, time emerges from perspective, not from consciousness in a mystical way, but from the physical fact that observers are embedded within space-time rather than outside it. Critics of the emergent view often object that it undermines causality. If time is not fundamental, how can causes produce effects? The answer is that causality does not require a fundamental time parameter. It requires consistent ordering of events along world lines. Relativity already enforces causal structure without invoking a global time. Light cones define what can influence what. Cause and effect remain well defined locally, even if there is no universal now. Emergent time does not erase causality. It reframes it. Another objection is that emergence sounds like hand-waving. If time is emergent, what exactly does it emerge from? This is a fair concern. Physics does not yet have a complete answer. Different approaches emphasize different underlying structures, such as entanglement, correlations, or geometry. What they share is a rejection of time as a primitive ingredient. This rejection is not arbitrary. It is driven by the failure of time to behave consistently across theories. Space can be quantized. Fields can fluctuate. Time resists both. That resistance may be telling us something. It may be that time is not something to be quantized, because it is not fundamental in the first place. Importantly, emergence does not mean illusion. Temperature is emergent, yet thermodynamics is one of the most reliable frameworks in science. Sound is emergent, yet communication depends on it. Emergent phenomena can be robust, universal, and indispensable. Time may be the most robust emergent phenomenon of all. This perspective also helps explain why time feels so central to experience. Emergent phenomena often dominate at the scales relevant to us. We live in a regime where time is unavoidable because we are complex, irreversible systems. At smaller scales, time fades. At larger, more global scales, it may disappear entirely. None of this implies that time is optional or arbitrary. It means that time belongs to a certain level of description, not to the deepest one. The deeper description may be timeless, but that does not make it more real. It makes it more general. Physics has encountered this pattern before. Classical mechanics gives way to quantum mechanics, not because classical mechanics is wrong, but because it is incomplete. Classical descriptions still work where appropriate. Likewise, time may remain indispensable at the level of experience, engineering, and cosmology, even if it is absent from the deepest equations. At present, there is no experimental way to decide definitively whether time is fundamental or emergent. Both possibilities remain open. What physics has done is show that treating time as unquestionably fundamental leads to contradictions when theories are pushed to their limits. Emergence resolves those contradictions by relaxing an assumption rather than forcing incompatible structures together. Whether this resolution is ultimately correct remains to be seen, but it aligns with a broader trend in physics. Concepts once thought fundamental often turn out to be approximate, context-dependent and emergent. Absolute space disappeared. Absolute simultaneity disappeared. Absolute time may be following the same path. This does not leave us with less understanding. It leaves us with a more nuanced one. Time is not gone. It is repositioned. Instead of being the stage on which reality unfolds, time becomes a pattern that unfolds within reality. If time is emergent, and if it arises from relationships, entropy and perspective, then what does that mean for how we live inside it? How do beings embedded in an emergent time experience continuity, memory and presence? Notice what is happening right now before any ideas arrive. There is a body somewhere supported by a surface. There is a rhythm of breathing that does not require instruction. There may be distant sounds, or perhaps a quiet that feels full rather than empty. After travelling through equations, theories and limits of understanding, the simplest fact remains. There is an experience occurring, and it feels like now. Physics does not often pause to acknowledge this. Its job is not to describe experience, but structure. And yet everything discussed so far ultimately circles back to this moment, because every measurement, every clock reading, every experiment ever performed happens somewhere, sometime, for someone. However strange time becomes in equations, it still arrives to us as presence. Throughout this exploration, time has gradually lost the qualities that once made it feel solid. It is no longer universal. It does not flow at the same rate everywhere. It bends with motion. It slows near mass. It fragments between observers. At the deepest levels, it may not exist at all in the way we imagine. And yet, here it is again, unmistakable, unfolding as awareness. This is not a contradiction. It is a layering. Physics describes reality at different levels, and time belongs differently to each. At the most fundamental level, time may be absent, replaced by relationships and constraints. At the level of space-time, time becomes geometric, local and flexible. At the level of thermodynamics, time acquires a direction through entropy. And at the level of experience, time becomes felt continuity. Returning to the present moment does not undo any of the science. It completes the picture. Consider what the present actually is, from a physical point of view. It is not a universal slice of the universe. There is no cosmic now sweeping across space. Relativity has removed that possibility. Instead, the present is local. It belongs to a world line. It is defined by what can influence you and what you can influence in return. The present moment is the set of events within your immediate light cone that are interacting with your body and brain. Signals arriving now left their sources at different times. Light from a nearby lamp left moments ago. Light from a distant star left years or centuries ago. Yet they meet here, now, forming a coherent experience. The present, then, is not a point in time. It is a process of integration. Your brain continuously assembles information arriving at different delays into something that feels unified. That feeling is not given by the universe. It is constructed by a physical system embedded within it. This does not make the present unreal. It makes it physical. Memory plays a crucial role in this construction. Memory is not a passive recording of the past. It is an active, energy-consuming process that encodes information irreversibly. Each memory formed increases entropy somewhere, exporting disorder into the surroundings. This is why memory points in one direction. You remember the past because physical traces of past events exist. You do not remember the future because those traces have not formed. The present moment is where memory formation happens. Anticipation works similarly. Predictions about the future are constructed from stored information and probabilistic inference. They do not access the future, they estimate it. From this perspective, the present is the interface between stored correlations and unfolding uncertainty. It is where the universe becomes informative to a particular system. Time, as experienced, is not something moving. It is something being updated. Each moment, your internal state changes in response to interactions. That change gives the impression of flow. But nothing external needs to flow for this to occur. The flow is internal, relational, and local. This aligns surprisingly well with the idea of emergent time. If time arises from correlations, entropy, and interaction, then the present moment is simply the region where those processes are active for you. Physics does not need to postulate a moving present. It only needs systems capable of recording, processing, and updating information. Where such systems exist, time appears. This also explains why the present feels continuous, even though physics, at some scales, suggests discreteness. Neural processes integrate over short intervals. Sensory data is smoothed. Tiny gaps are filled in automatically. Continuity is an emergent feature of perception. The now you experience is not infinitely thin. It has duration. Studies suggest that conscious integration occurs over tens or hundreds of milliseconds. That interval is your experiential present. Outside that window, events are either remembered or anticipated. Inside it, they feel immediate. This experiential present is not fixed across species, or even across states of consciousness. Alter attention, fatigue, or chemistry, and the felt width of the present changes. Time seems to slow or speed up, not because external time changes, but because processing does. Again, time reveals itself as contextual. What is striking is how gently all of this fits together. The physics that dismantles absolute time does not erase experience. It explains why experience is local, directional, and grounded in change. Returning to the present moment, then, is not a retreat from science. It is a recognition of where science meets embodiment. Your body exists along a world line. That world line accumulates proper time. That proper time is what your cells, your metabolism, and your nervous system respond to. No matter how time behaves elsewhere in the universe, this local time governs your processes. Even if the universe as a whole were timeless, your experience would not be, because experience requires change, and change requires difference between states. This is an important distinction. A timeless description of the universe does not imply a timeless experience within it. The two operate at different descriptive levels. A map does not move, but a journey occurs within it. From this angle, the present moment becomes something quietly remarkable. It is the point where a timeless structure gives rise to lived continuity. It is where relational physics becomes felt reality. Nothing about this requires mysticism. It follows directly from the way complex systems behave. As you rest here, listening, breathing, perhaps allowing the edges of attention to soften, you are participating in this process. Neural activity, chemical gradients, electrical signals, all unfolding according to physical law, all creating the sensation of now. The universe does not need to know what time it is for this to happen. This realization can be oddly comforting. If time is not something racing forward independently, there is less sense of being chased by it. What exists is this ongoing update, this continual integration of information. Moments do not rush past, they are replaced. Even the language of passing is misleading. Nothing leaves. The system simply transitions. Physics often strips away familiar metaphors, not to leave emptiness, but to reveal quieter structures underneath. Time, once stripped of its imagined flow, becomes less threatening and more intimate. It is not an external pressure, it is an internal process. This does not mean deadlines disappear or clocks stop mattering. Those are practical tools built on regular processes. They remain useful, but they are no longer mistaken for the thing itself. The thing itself is change. relation, and accumulation. As attention rests in the present moment, there is no need to hold on to conclusions. The science does not demand belief. It offers perspective. You do not need to decide whether time is fundamental or emergent to notice that this moment is happening. You do not need to resolve the problem of time in quantum gravity to feel the weight of your body or the cadence of breath. Physics has done its part by loosening assumptions. What remains is simply being here. And being here is not static. Even now, micro-changes are occurring. Cells exchange molecules, neurons fire, signals arrive, records form, entropy increases slightly. Time, in the only sense that matters locally, continues, not as a river, not as a ticking background, but as an unfolding pattern of relations. There is nowhere this needs to go next, no final answer waiting. The exploration does not end because the present does not end, it refreshes. As this settles, you may notice that the question of what time really is has softened. It no longer demands resolution. It becomes something to live inside rather than solve. Physics at its best does not close experience. It opens it gently, making room for curiosity without urgency. So for now, let the present moment be what it is. Not a point on a timeline, not a fleeting instant, but a living interface where structure and experience meet. Nothing more is required, and nothing has concluded.